Fire Pinto, please check our audio. Iron Man's gonna get you. That's Paul. That's my. That's Fong's son. They live next door. Currently, they're moving though. Okay. Audio check, Fire Pinto. Audio levels. Alex, give me a MC check.
Check 1 2. Check 1 2.
Good. They look pretty well. Fire Pinto, can you hear an echo? Go ahead, Alex. Say it again.
Check 1 2. Check 1 2. Hello.
I just want to see if there's an echo this far away, because I'll turn my mic down if I have to. Actually, I can turn your audio down a little bit. Okay. So I have no echo. All right, cool. So I'm gonna actually make this camera a little better. Not like it used to be. All right. So let's do a quick introduction of what we're doing and let it rip. So let's see more video. All right, cool. Hi, Alex.
Hey, Russ. How you
Good
doing,
morning.
man?
Gries Petty Research Workday. Really quickly, I wanted to make a short video for the real channel and not just the live stream channel. Alex has been playing around with his cells, and he's going to show you what he's been doing. I'm going to just briefly show you what I did last night really quickly, which was take these cells that I have. So I currently have these all connected. As you can see, they're connected in series. All right, all 6 of these. This is an extra one. Everything is plumbed with movable water, so the water is actually moving through the cells. So if I turn this voltmeter on right here, you know, I'm currently running water through the system. It's going through this cell and then through all of these cells. These are all hooked in parallel. This one's running in a daisy chain as series. So, so electrically connected in series, plumbing is connected in parallel. So right now, a reading across this extra cell is 0.75 volt DC. Currently, I'm sitting at 0.571 volts DC across these particular cells. So, I think what I'm going to do is set this here so that you can actually see the meters. Turn the light on that one, maybe. Okay, so there you can see the meters. So what I'm currently going to do is just energize. I'm going to turn the pump off. Water's not moving anymore. I'm going to currently energize these cells with 30 volts DC. Just because that's what I have maximum voltage currently available to me. So crank it up. 30.1 volt. I'm not seeing any current being drawn. This is distilled water, 0.00 amps on this particular meter. I'm sure it's pulling a tiny bit. Absolutely no gas production. Okay, so now I'm going to, I got 30 volts, so now I'm going to disconnect that, and you will see it's holding a very nice potential. It's holding 11.3, 11.2, 11.1, all right. So the cool thing about this is I can actually take an LED as such, all right, and hook it up with the correct polarity, of course, and it will light the LED. And it will light the LED actually for a pretty good amount of time. Alright, so we'll let it sit here for a minute. So I'm currently lighting this LED, it's discharging. Now here's the interesting thing. I can still move water through here and it does not change a single thing. So if I turn this pump on, alright, pump is on, I'm pumping water through the system, and nothing special is happening here. There's no energy loss, more or less energy loss. You can see it's still the exact same discharge rate. So I find that rather interesting. So that's my quickie experiment. I thought that was kind of cool. And I'm going to give Alex the floor because Alex can disassemble his cells. And so I'm going to let him take it over. So Alex, I'm going to give you more full screen.
Hey guys. So yeah, a lot of what we're doing here, you can see also in the capacitance post I made on my blog. A lot of the results that Russ just described are also described there. So the results are, they're definitely repeatable. Anyway, it's not clear that anything we're doing here is particularly special, but it is interesting, and it's just we're trying to get our head around what the behaviors and characteristics of these capacitors that that we're building, what they're all about. And so from that level, these are all just interesting baseline tests. Now what I'm going to do here real quickly is just show you that I've got these two identical cells, these two identical stainless steel capacitors that we're going to be using distilled water as a dielectric. And you guys unfortunately can't really see, given the quality of my camera and the distance of it from. I need to get a better video set up so that we can have multicams going on. And you can really see the equipment and so on. But I'll just describe to you what I'm doing. So this is my voltmeter, and this here is a 120 volt power supply capable of 2.5 amp current. And it actually goes up to about 132 volts if you max it out, but I usually don't pump it too much over 120. Anyway, these two stainless 304 stainless steel capacitors are identical, and right now they're just indicating kind of an electrically neutral condition. They're just sort of the voltages are just kind of random and in the millivolt range, switching from positive to negative. Now, when I put this thing inside of distilled water and then energize it. First of all, as I put the water in it, the voltage range changes from where it was in the 0.02 millivolts DC to now it's in the like -11, -12 range, and fluctuating around. Now, once we energize the capacitor, however, it's going to be, everything will be, the polarity will be quite certain, and it will be, well above a millivolt range. All right, so let me just turn this on. All right, so now I'm increasing the voltage, 25 volts. I've noticed that the cell will not produce anything until about 70 volts DC. So right now I'm at 50 volts. I'm at 50, my voltmeter is connected. So 60 volts, 70 volts. Now I'm starting to see a little bit of bubbles, but very little bit. I'm continuing up towards 90 volts. And really, those bubbles actually, yeah, there's definitely some little tiny bubbles for me. I'm at 101 volts. I'm at 110 volts, 120 volts. What the hell? I'll crank it all the way up. 133.24 volts max current. So there it is. You can't really see the water is kind of it's not really bubbling at all, actually. I mean, just a little bit. I can see bubble formation on the plates, on the cathode. I see some, but it's really not, So I'm just gonna let this charge for just a minute. Give it a nice strong charge. Maybe I'll turn this back down. I don't want to blow my. I'll turn this to 120 because that's what it's rated for. I'm at like 110%. So we're letting this steady current do its polarizing work on the water itself, and we're also polarizing the plates themselves. All right, so maybe that's enough for the moment. I want to shut this guy down, and now my voltmeter, is still connected, so we can see it's going to fall down to a level I've noticed between 2.1 and 1 volts. And then actually, let me turn this guy off and disconnect this. Now it falls directly to 1.9 volts, and then after that, quickly to 1.5 volts. And now it's at 1.4 volts in discharging. Okay, so the interesting thing here is if I then short this guy out, if I then just short him out completely by taking these two ends and just putting them together like this. So now I'm back down in the millivolt range. Okay, so now if I reconnect this to the voltmeter, We go, I have them backwards, but we're at 1.1 volts. So now we're back at 1.1 volts DC and discharging. Okay, so now if I take this out of the water capacitor, I mean out of the water bath, okay, and just make sure it's all empty of water. Take it apart even, you know, kind of dry it off, touch the plates together, everything. And then we again look at, so now it's, you know, more or less dried off, and I'm gonna see what the voltage is on this thing. It's now charging itself back. Okay, so now it's at 1 point, sorry. So now the voltage, well actually in this case we got a different result. This time the plates really discharged fully, which is very different from the last result I had. But that's okay. Let's see. Well, it's now, no wait, it's climbing again. Now it's 0.1, 0.6. Okay, so basically it is climbing back up. But last time I saw it climb up faster.
Maybe Alex, maybe something was shorted temporarily that you couldn't see, possibly.
Well, no, it's charging. It's just charging a lot faster than it did before.
Okay.
I'm sorry, it's charging a lot more slowly than it did before. So now let's put it back. Let's put it back in the water just to see.
What was that voltage?
The voltage on the meter was, hold on, it was at like 0.25 volts and charging. But before I saw it jump up to right back up to where it was. So that's not sure what accounts for the difference. It's weird. But anyway, you can see those other results in my blog. So it's weird to have inconsistent results, and I don't like that, but it is what it is. So I put it back in the water, and it jumps, and now it's jumped back up to 0.55 volts, and it's discharging along the same curve as before. Now I'm going to take the this other capacitor, which is electrically neutral, that hasn't been charged up at all ever actually, and just make sure. So now this one here is at, you know, kind of oscillating at just between, anyway, it's in the millivolt range. It's just kind of random polarity. And I'm going to put this guy in the water, which has the water has the charge. So this will hopefully tell us what the charge just in the water alone is. What I was seeing before was there was a charge on the plates and a charge in the water, and that they kind of summed together. But that effect, given the result I just had a moment ago, was less pronounced. So, okay, so now I'm putting this guy in the water. Oh, I'm an idiot. The reason we got no voltage last time is because, oh no, never mind, I'm sorry. I'm not an idiot.
That happens to the best of us. So that one wire,
Yeah.
we always tend to forget to hook up.
No, but I did hook it up. It wasn't that. Well, just getting very different results than I got on the last series of tests. I'm not sure if it's because I energized, but anyway, this time the electrically neutral in the water is not indicating much of a voltage at all. So the only difference I can think of here is that I energized the water a lot longer last time. I don't know. But right now the electrically neutral capacitor in the water is still really showing electrically neutral. In other words, the charge in the water is not imparting much of a charge to this unenergized series of plates. So just as a final test, let's see what this other capacitor is doing, the one that did receive the charge. Every test is a good test, even if you don't get the results you thought you were going to get.
That's right.
But it's true.
Uh-oh. Lost your Skype feed. Oh, yes. Gots to love that Skype. It's such an awesome thing.
What happened? Oh, okay.
Okay.
So now we're back with the with the plates that had been charged, and it's reading at 0.45 volts, so it's still discharging, and what that tells us is it's really because I believe it must be the plates themselves. Well, let's take it out and just look at it again, because when I put the electrically neutral one in, so now we're looking at it again. When I take it out of the water, it's at it's like 0.21, 0.23. It's charging. It's not in the water. The charge is going up, 0.27. 0.28 in that area. Now I put it back in the water. So we got, now it's at 0.41. So there is that summing effect kind of going on, but let's see if we can get a measurement with the electrically neutral one. Let's see what we got here. Electrically neutral one is not registering anything. So oddly, when you take the charged capacitor, this one, out of the water, it reads a lower voltage that continues to discharge. When you put it back in the water, its voltage increases by 2 almost. So just to finalize that test.
Yeah, and also, like, to confirm like what you just saw, and then the results might be different because of the charge time.
Yeah.
But to confirm kind of what you just saw and what I've been doing, I have my meters here currently. They've been sitting untouched this entire time that you have been discussing, and what I'm seeing is the particular voltmeter right here is connected to that cell, which is this empty cell. Well, it's not empty, but it's not daisy chained with the rest of these. And it has not changed its voltage whatsoever. So if I charge up, if I disconnect this LED again, and I connect this, if I connect this cell back up, all right, and it's at 30 volts, there goes 30 volts. This voltmeter, if the water is being charged somehow, this voltmeter should be showing some extra voltage. So in this case, I'm not pumping any water. So let's turn up the water pump on. All right, water pump is on. And you can basically sit here for the rest of the day and you will never see any extra charge show up on these other 2 plates. This other cell that I'm being, the water's being ran through it. I tested this yesterday for quite some time and could not see any different in voltage here. And then again, we can disconnect the power supply, reconnect this LED, and it will glow. Now let's short out the water cell. Okay, so I'm dead shorting it. All right, you can see I shorted it. Take it back off. Back up to 4 volts. See if the LED still lights. Yes, it does. So effectively, what Alex and I are showing here is that the plates really do hold all the potential. The water doesn't necessarily hold much of the potential. And of course, charging it for a longer rate may change the effects according to some of Alex's previous work.
Yeah, like if you look at my blog post, you'll see that, some of the results I got before after having charged the water for significantly longer periods of time seem to suggest that the water was in part holding some of the charge, and I could measure that charge by putting in the neutral capacitor, which had never had charge applied to it, and by submerging that, I was reading a voltage out of nowhere, and I thought it must be coming from the water, and but just now the test that we did not really confirm that result. So it really may have to do with the amount of time that we charge. Now, as we've been talking, this capacitor that had been charged a moment ago has been its charge has been climbing. Not too high though. It's at 0.3. Since Russ started talking a moment ago, it was at 2.20 volts, and now it's climbed all the way up to 0.34 volts. So the charge in the plates is just climbing for whatever reason, but probably because we charged it, we applied charge to it, and I don't know why it's charging up right now. I mean, I'm not sure what about unless the voltmeter is playing a factor. Although I looked into that point, and the voltmeter doesn't really apply a voltage. So there's that. Now going to this other cell that has never been connected. This other capacitor has never been connected to power. It's just sitting here. It's going down and up and everything. While this one, after having been taken apart, and I'll take it apart again, but here it is at 3.36 volts. I can take this one out, and now look at that. It's completely separated and still showing a voltage across it. It's even a higher voltage across it, 0.5 volts. So it makes me wonder if it's not the test equipment. But 0.38 volts, if I take them apart, now it's at 0.5 volts. It's pretty weird, huh?
Yeah, it's just an interesting kind of overview of the differences when you take apart cells. Now, according to some other thoughts, you can do the same. You can do a very similar thing with a linen jar. You can charge a linen jar up to a super high voltage. You can take it apart. You can touch the plates together. You can do whatever you want. You put it back together, and you still have a relatively high potential there. So currently, I just, while Alex was talking, I disconnected the LED, and the charge kept going back up. So let's see if this LED will light again. Yes, indeed, it will. And it's dim, but it is lit. So anyway,
the fact that we were at a higher voltage when we took the cells apart, that's a really strange result. I hadn't seen that one before.
When you disassemble them?
Yeah, and the voltage got higher. That's a pretty weird thing. Anyhow, well, so clearly, it seems to be the plates where all the charge is being held, and I think the charge in the water might be maybe at a minimum.
Yeah, I'm still not seeing, after leaving this pump running, I'm actually seeing a lower voltage, like it's a more neutral voltage than before in that one single cell that's isolated by itself electrically. So
one last thing, this capacitor that's neutral, it's never been charged up with the power supply. When I put it together and measure it, it has a neutral kind of, it's kind of millivolts, positive and negative polarity. Okay, and then when I put them together, it's at 0.3 volts together. This one hasn't been charged. Yeah, so these results are just on the bench right here. I'm getting very inconsistent results here. So anyway, maybe that's helpful, but probably not.
Well, read Alex's blog for what he did do, and let's try this test again and charge that thing up for a while and see if you get the same results, Alex, and we'll tag it onto the end of this video if you get the same results as what your blog post is already describing.
Yeah, that would be good.
All right, well, there you go. Gries Petty Research will continue all day today. It is Friday, the 31st. Happy Halloween for those of you who celebrate. I'm wearing my hat today. A little scary, I know. Alex is wearing his hair. It's weird. So anyway, all right. Well, peace and love to you guys. Have a good day, and that's it for now. Any last words, Alex?
No, that's it. Thanks very much, guys. Have a happy Halloween.
All right. See you guys. Cut.
Man, that was like the results of that test were really all over the place. I'm gonna try this again.
Yeah.
Now I'm very curious.
I'm still recording. I haven't it's gonna be recording all day. So just charge that sucker up for a while and see what you get.
Yeah, that was just really strange. So I'm gonna the only difference between the test series was it had been charging for, I don't know, it had just been charged all day and during tests. One had. The other one, the electric neutral one wasn't charged ever. The electrically charged one had been charged, for a period of hours while I worked, while I did a large series of tests while I was trying to get a handle on exactly what was going on. And just now we saw none of that. And so the only difference, I believe it really must have something to do with,
The time charge of water.
yeah, the time that you apply the charge, not just to the water, but to the plates as well.
Yeah, yeah. I think you could. I think you could charge the plates outside of the water, and it would react almost identically.
Yeah, I think so. I mean, absolutely, no doubt.
Okay, Fire Pinto. I've connected the LED across the cell that has nothing, and I'm charging the water bath at 30 volts, and I'm getting absolutely nothing. So I believe this meter is right. 0.61 volts DC, 61 millivolts. So, okay, that test is complete. So, moving on, I would like to set up the frequency generator that we created and play around with it and see what happens.
The really weird thing here is the voltage across these plates, even when they're nowhere near each other, is reading higher. Well, now look at that. That's really weird. If I move them far enough away from each other, like that far, can you see what's going on here?
Yeah. Well,
when they're this far apart,
yeah.
it's millivolt range. But if I move it here, now it goes up to 0.29 volts. If I move it here, 0.4 volts. If I move it here, it's 0.34 volts. So it's like, what the hell? There's like this field effect going on. That's just bizarre to me.
It might be external, like capacitance with yourself.
Well, it's clear. I mean, this is just the DC voltage between them. At this distance, it's like a short. There's nothing. But at this distance, there's, you know, a third of a volt. And at this distance, it goes down. Isn't that odd? Is that just a test measurement issue?
Maybe check all your leads. Check all your leads again and double check everything, because I know every once in a while one will be rubbing the other or the wrong way, and they'll get mad at each other.
No, man, this is like a straight line. It's like two probes with alligator clips, and I'll reconnect everything. Okay, so there, 0.38 volts at this distance. At this distance, nothing. At this distance, 0.27 volts. If one inside the other.
Hey, Fire Pinto said to try hooking up your scope and seeing if you're seeing any, 60 hertz sine wave stuff going on where you're using it as like an antenna, not meaning to. Hey, do me a favor. Turn your camera to where the edge of those boxes. No. Put it back. Turn it left and right. Pan. More. Oh, right there. Because this way I can truly give you complete half screen and you're all in the shot. Perfect.
Okay.
That's better if you're more full screen. So.
Yeah.
I'm just trying to figure out the best. The whole thing is camera view. Yeah, so keep doing whatever it is you're doing. I'm gonna start. Yeah, I'm gonna start setting up my other test stuff I'm gonna do. But
you can just edit my whole portion of that video out. There was really nothing of value there. It was just inconsistent.
Well, we can. We don't have to use it either.
Yeah.
Either way, it'll still be on. It'll still be on the live feed recording YouTube channel, but I won't.
That's okay.
If we think it's not worth publishing our results because they were not consistent with your prior results, then we won't.
Yeah, I don't think we should. I want to figure out exactly what's going on here. And right now I'm very. I mean, like right now, this cell is sitting here with a higher voltage. This was the one that was charged with a higher voltage than it had. It's at 0.34 volts right now. It's climbing. And then if I put it over here, and then as far as Fire Pinto's question on, let's take a look. I mean, there's a huge 60 volt. There is a AC
sine wave, but you know what? That sine wave that you're seeing, I've seen almost on every single thing I can put my hands on in my shop. So I can't tell you that that's what the real problem is, though, that you're seeing.
Well,
that's the problem.
Let me go get an earth ground and attach it and just see.
Oh yeah. Yeah, do that. I'm gonna crank up my music. It's awesome. It's like it's gonna override the video. I need to slice a file. Start a print. Sweet, Fire Pinto, my settings were indeed saved on my printer. I turned it off, turned it back on, and they were saved. You got to enable that function. I was not aware of that originally. I am now.
Yeah, so when I touch an earth ground to the cell, I mean, it's gone. The sine wave disappears. So it's just.
Wait, say that again. Hold on, too far away. Say it again.
Sine wave disappears when I put an earth ground on the cell. So let me see something. Let's see what the voltage does, though. Let me see if that voltage disappears. I was just measuring the DC part of an AC sine wave. That'll make a lot of sense. All right, let's see.
I am going to temporarily quit sharing my screen. Because it just kills this thing. Trying to slice a file so I can print something. Wow. Is my video still even live? Well, it's still running. Oh, Alex, can you still hear me?
Yeah.
Hold on, everything is just so bad.
I wish you could see my scope. Like there's okay, so
I can kind of see it.
okay, so there's the sine wave. When I apply, that's the cathode. When I apply the, hold on. So when I apply the ground to the anode, you know, that's the phase, that phase velocity, the phase, that AC part of the AC just goes away, just grounds it out. And then if I do the opposite test, yeah, I mean, I ground out the cathode, then that sine wave on the anode goes away. And then as far as volts, interestingly, it's reading negative volts ever since I touched the ground to it. It's in the polarity changed. Let me see the other one. Sine wave still there. Yeah, so whether or not that this ambient 60 hertz, or I think it's 60 hertz sine wave is there, it doesn't seem to impact what the voltmeter's telling me in terms of DC voltage. Whether or not I ground it out, or at least it does. I can't see the difference in measurement quickly, but it doesn't appear to create a difference. Obviously, it must have some difference, but
Yeah.
Well, the other thing too is, right now I'm in the order of 0.2, 0.3 volts charging, whereas before it was like close to a volt. So something is very different about this series of tests. I'm going to charge up the water for a good long while and see what that's about.
Okay.
I can't see your screen anymore.
I turned it off temporarily because I need to slice a file and I can't even hardly move my mouse around.
Okay, got it.
So I'll turn it back on in a second.
No worries. This was letting you know.
Yeah, thank you. Man. Firepinto says, so from these tests means the electrostatic filter has no effect on the resonant chambers or vice versa. I'm going to say that's correct, but as Alex described earlier, when you pre-charge the water or try to do whatever you're doing with the water in that manner, it can change the resistance value. Is that correct?
Yeah, it does. It lowers the resistance.
So we'll have to So
Charged water has lower resistance.
I would like to actually physically check that. I can introduce a potential in that one cell, and it will charge the water flowing to the other cells, and I can just measure resistance and see if it changes.
That's exactly, if you look on my blog, you'll see those exact test results. But yeah, you should try to confirm them.
Ooh, did you hear that?
I hear a violin.
Oh yeah. Here, I'll turn it up so you can really hear it. Oh, its song's over. Too late. That was Lindsey Sterling.
Yeah, like it goes from there. I'll pull the results for you real quick.
Yeah, I need to read that entire post actually, but I've been focusing on this darn printer. It must get done, and I'm pretty excited that I got it far as I got it.
It's yeah. So before charging, let's see. Before charging, the resistance was, basically 2 to 2.3 kilo ohms, 2 to 2.3 kilo ohms, and 11.1 mega ohms DC. Then after charging, the resistance was about 1.2 kilo ohms, and the DC resistance went to 1.3 mega ohms, so down an order of magnitude. And then after an hour, they went back up to, not all the way back up, but they were heading there. So those results seem to suggest that charged water offers less resistance, which intuitively makes sense because it's like the pathway is set,
Yeah, it's already polarized, if you will.
Yeah, yeah.
So maybe you should charge that cell and go wind some coils and come back later and see if you're seeing the same results.
Yeah, I'm just I want to establish a really, 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 really clear baseline because I don't really want to understand because before I spent hours on testing and I was pretty clear. Oh wow, this happens every time.
Right.
And just now I got a whole series, the results that just got made no sense. And the only difference is that it was pretty. The bench was cold, really.
Fire Pencil says an ohm meter is supplying voltage to a circuit.
Yeah, so.
Which it does.
It does, yeah. And we're applying ranges of AC to it. Between 100 and 10K, 100 hertz to 10K. I mean 100 ohm volt. What am I saying? 100 hertz, yeah, 10K.
I love it when I do that. I'm like,
yeah. 100 ohms, 100 hertz to 10K hertz. That's what we test. That's the range we test across, and our meters do introduce a small voltage, but when we're measuring ohms, we're not really looking at the volts. And then I use a fluke meter to get my measurement on the ohms, the DC ohms, because it seems to give me the best results.
Fire Pinto, can you hear an echo from Alex still? I'm going to turn my audio level down even a little bit more, like that, to get I'm really trying to get our audio levels matched. I don't think they ever have been perfect. They've been pretty good, though, the last couple times. But that one video, I think 2 weeks ago, was horrible. The ones before that were great, and I didn't change anything, I don't think. I'm trying. No, it sounds good. Fire Pinto, how do I enable the fan to blow all the time at full speed in K-Slicer? Can't figure out and why it doesn't. It should run all the time. Fire Pinto says, I really don't mind the echo. Gives it more
more sci-fi.
Gives it more sci-fi. Fire Pinto. Oh man.
Makes it seem like I'm orbiting in a space station or something. Yeah, man. So it's just sitting there with 2 points. I don't know. It's pretty consistent. The electrically neutral, the one that's never been charged, the cap that's never been charged, just sits there with no voltage. Can't even get voltage by putting it in the water. And the other one has voltage whether or not it's in the water, and it has voltage even if those plates are anywhere near each other, within a few, if I move them more than like a half a foot or so, then it finally doesn't register anything. But if they're within a half a foot of each other, they show a voltage across them, even though there's a huge amount of air between them. Bizarre.
That's kind of odd.
It is very odd. It's a result that I don't quite believe that result. Oh boy. Well, I'm gonna charge this bad boy again. I'm just gonna let it charge at like 60 volts for quite a while. $60 volts, and I'm gonna run it through my ammeter.
M106. I'm just going to enter it. Oh, I'm typing on the wrong keyboard. Oh, I want to do full speed though. Till 256, 255. M106. S. Isn't it 255? Yeah, 255. Yeah, I'm in full value, 0 to 255, but so if I set the fan on at the beginning and I'll turn it off at post fix, but the thing is I don't know if if the software is constantly enabling or disabling the fan throughout the entire process, because I have another place where I can say fan cool loops inside cool, and I have a value from, let's see, while extruding loops perimeter and crown, set the fan to this duty cycle, and they're all at 100. So the fan should be on every single time, and it never is. While extruding everything else, set the fan to this duty cycle. If slower, a layer to reach in layer S, make sure the fan is at least at this duty cycle. And I've always set those at 100% and the fan never runs. So I put it at prefix and postfix to turn the fan on and off. So let's see if that fixes my problem. Just give it a shot and see what happens. So save this and just see what happens.
Alright, so I'm just going to hang out here at 55 volts.
No, it's 0 to 100% on my sliders. What's that?
I'm just going to let this thing charge at 55 volts for like an hour.
Okay.
No amps are going across it that I can measure anyway.
Any gas production?
Let's see.
Minuscule amounts? Because I can't even tell on mine at all. Like, they don't even produce anything.
Yeah, definitely minuscule amounts are being produced right now.
See, originally, remember when I did my test and I hooked it up, I was getting bubbles?
Yeah.
And I put brand new, fresh distilled water in there, and now nothing. So it's like over time, somehow, somewhere, I gathered contaminants.
Probably from the plastic materials.
I
The
guess.
yeah, it's interesting. I don't know if you can see this, but it's very cool. You can, as the water, you can see how as the bubbles form, they kind of move like in like a within the lines of force, and then they like magnetically snap themselves to either one plate or the other, depending on whether or not it's oxygen or hydrogen.
Yeah.
And that's kind of nice to, it's just cool to see. It's just
You
cool looking.
you can see that on yours?
Yeah, like I can just look at it and I can see as the bubbles form, they kind of like battle it out in the lines of force and move in weird ways until they finally like magnetically snap to one or the other plate.
Nice.
I'm watching that as we speak. It's cool looking. Maybe I can show you if you want to see it.
Yeah, try it.
Let me put a light on it.
Should be able to see my screen again.
Ooh.
I'm going to use the restroom. Hold on. I'm back.
All right, I'll try to show you this effect. I don't know if you can see it or not, but
I is watching. I think we tried this before, and I think this particular camera doesn't focus this close.
let's
try
see.
try it again anyway. Is it inside the cell?
Sorry?
Is it inside the cell I'm looking for?
Yeah.
Oh man, I don't know if I can see that.
See if I can get it there.
Good morning, how are you?
Make your ugly stuff.
No. I'm a failure. Actually, I didn't have the recipe.
Is it blurry?
I have to get it from my dad. It's not blurry, but... Well, it's kind of blurry, but like...
You won't be able to see the bubbles, I guess.
No. Maybe you should record it with your good camera.
Yeah.
And post it somewhere so everybody can see. It's kind of cool. Not today.
Okay.
Ooh, you're all fancied up for a cold day.
Jacket? Yeah.
Enjoy. Okie dokie. Yeah, so this morning on my way up, I heard this loud popping noise, and
Yeah.
my moped was, my headlights got real bright, and yeah, I don't know exactly what happened, but my battery was completely dry, and I burned up the charging apparatus I designed. It's a little pre-made circuit board,
Yeah.
and it got so hot, it popped, and that's what I heard that through under my helmet over my motorcycle or moped noise. I heard it pop, and check out this view on my camera, on my screen. See that? Hold on, let me. There, you see that?
Yes.
That's the chip that was on the circuit board that's now melted into the lid that I had made. It got so hot, it melted off the circuit board onto the lid and cracked open.
I wonder what happened. That's crazy.
Well, it overvoltaged. It was sending an AC current. Blew out the it blew out the filter capacitor, and just all of it went into the into the other thing. Kind of, yeah, it's awesome. I was like, okay.
So is it going to easy to repair it for you?
That particular part, I just pop a new board in because that's a pre-made, assembled Chinese $2 board. So yeah.
Good.
Luckily, I bought a few extras.
I guess it didn't prevent you from running, so that's good.
It was still running, and the headlight was still on, and everything else was completely dead. So I was lucky because it was dark this morning. All right, Fire Pinto, the fan is on. Let's see if it continues to run. That is the question. Although Fire Pinto said he turned his audio off because he went into the classroom. What's he say? I'm back, he says. Okay. So I have not yet, and I need to send out this email. Yeah, it was very interesting. I heard it pop through a casing of 3D printed plastic, the casing that my headlamp and whole entire housing is in, through my helmet, through my cap that I had on that's a cloth to keep my head warm. I heard it pop through all that. And over the wind noise and over the very loud muffler noise. Like, that's ridiculous.
Yeah, that is.
That's a loud pop. I'm hoping that's what I heard pop, and it wasn't something I'm missing, but I'm pretty sure that that's what I heard. It's so loud. I thought it was a rock hit my helmet. That's how loud it was.
Man.
I was almost... If my headlamps wouldn't have gotten brighter, I would have almost been certain, oh, that was all I heard. But
Is
my
there
headlights...
is there a little capacitor in that thing?
There's a tiny little capacitor in the circuit board, and it's
Yeah, that's
like,
probably what blew up.
well, you know, it did blow up, so maybe that was the pop. And then the other part that I heard was the chip, but the chip was cracked in half too. At one point, I've heard pretty loud noises from ICs exploding, but not like that. That was really loud. It almost had to be the capacitor.
Yeah. Usually the ICs blow with a little fizzle, like.
Yeah, exactly. You can see it definitely did have a fizzle explosion.
So yeah, I've been applying 55 volts even to this thing for a while now. I'm starting to get some brown guck because I don't think I've ever applied this much DC. Like last time I did it, it was like I spent a lot of time charging at much lower voltages, but I just wanted to give this a good charge. Now I'm starting to get not too much, not really brown gunk, just a little bit of like I can definitely tell there's some electrochemical stuff going on, leaving some kind, leaving some residuals in the water. I'll let that go for a while. Here's what the, I don't know if you can see the waveform, but it's kind of like,
I can kind of see it from here.
it's got like little spikes in it. It must be, the power supply must be doing some kind of switching because I'm getting some ripple, I'm getting some spikes in there. This is a nice power supply, this Hewlett-Packard 6443B. It's like, it's not a switching power supply, it's like old school.
Oh yeah, from that one, from directly AC/DC rectified, probably filtered, and that's it.
Yeah, exactly. I can get, if I put the ground on the cathode of my cell here, I can get rid of most of the sine wave part of this. It cleans it up a lot. Oh yeah.
If you put it on the ground.
Yeah, I put the cathode on the ground and it does two things. One, very much cleans up the waveform. It's almost pure DC at this point. And also it seems to invigorate the bubbles a little bit too. Interestingly. Doesn't change the voltage at all, but you wouldn't think it would, but all right, let's see what that does. I'm gonna stop charging here.
Okay, finally got here. Oh, no. I have so much footage to edit. Yeah.
Yeah, it must feel kind of overwhelming sometimes.
Well, it's a good thing that I have this much footage, because now I just need to sit down and take the time to edit and make good quality videos, because I could put out a really crappy, long, stupid video right now, or I could take my time and make it amazing, all with the same footage, you know?
Yeah. All right, so after having charged this now for a good 20 minutes, I'm going to turn this off. Voltage falls immediately to 1.5 volts DC, as expected. And I'm going to immediately take it out of the water. First, I'll just try to earth ground it and see. Yeah. Doesn't mess with the charging curve at all. Okay. So taking it out of the water, it's like half the volt. It's like we're 1.5 volts to 0.7 volts. Let's see what the electrically neutral one does now. Actually, let me first see if this weird thing happens again. Point 5 volts. Still 0.5 volts. Okay. That seems to be the plate. Alright, that's the charged one. Got a half a volt over there. The uncharged one. Nothing. Put it in here. Still nothing. That's good.
Pretty bad when you build something and then you have to go back and figure out how to make it work again.
But understandable. It's a pretty complicated thing you got there.
This circuit I got. Here is this circuit. This is the...
Okay, so the electrically neutral one is now in the water. And it is charging, but very slowly. I'm going to let it sit there for a couple hours and see how high it goes.
Okay.
It's charging in the water. So, I mean, it's definitely but at the same time, the water is probably discharging. We'll see where it all where it all settles out. This is definitely different from last time, and that's concerning to me. That I would get such different results with the same experiment.
Yeah, that's not really a good thing.
Especially when it was a repeatable experiment in one day, and not a repeatable experiment in the next. It's just odd. Whatever. Oh, look at that. Let that go for a while.
Still sitting at 3.4 volts across that cell. It's holding.
Yeah, it's good. If I had left mine all, if I leave mine sitting there, the 1.5 volts will hold for quite a long time.
Yeah,
it'll take hours to discharge.
I'm currently seeing that. I am walking away from my computer for a minute, so I can't hear you.
Okay.
Trying to
Probably,
find some.
you probably didn't hear me say okay, but that's okay.
Let's see if I can. Ugh. All right.
Let's open it up for you. Yeah, I'll be right back. My son's Halloween costume just came, and I want to get it opened up for him.
Okay. I'm going to stop sharing my screen for a moment so I can send out this email too.
Cool. Right back.
All right. Need to plug that printer back on too. Hi, Electro. Just currently putting together my resonator circuit back together originally. Test some stuff. I'm gonna build a little quick box for it. Let's see, break out my old book.
Yeah, Diet Coke's the worst. I get it. Hola.
Hola.
Okay.
Hola. Oh, oh la la.
Hola la.
Oh la la.
That's the Spanish hello. Hola la. Yeah, so that if it's charging, it's just the impact of the charging on the water on the capacitor is so slow. Still like it's just 99 millivolts. It is still charging though.
In the water bath?
Yeah. Before I saw it happen very very quickly, and now I could see it right away. Like it would impart.
But I wonder if it's because the water, you only charged a tiny bit of the water. You need to let it sit and charge the whole bath after a while.
I guess so. Maybe I'll, well, the other thing is, I'm gonna try with the other power supply. That's a big difference right there.
Oh.
Shouldn't be a big difference, but let's see if it is.
I need the other parts. Splork. We'll see if he shows up, Mr. Plork.
Good old Plork.
Oh, man. Oh, mean. Alright, so I am trying to find my original stuff here.
Yeah, let this bad boy charge up. With the other DC, with the switching power supply, maybe there's some kind of difference. I don't know.
Almost sounds like it.
I just don't understand what difference it would be, but
It would be the difference that it is, my friend.
words of wisdom.
Let's see here. Sharky! Dude, look what I broke out today. Look what I broke out today, and I'm trying to remember where to hook everything back up. Woo! I'm assuming that's the same Sharky. I'm currently on your thread trying to figure out where I plug this stuff back in at. I forgot.
Alright, well, we're chilling out at 30 volts here, so I'm going to let it charge for, I don't know, quite a while.
Okay.
No amps.
Wow, this file's been downloaded 1,730 times.
Which file?
The file of the schematic that I'm working on, which is the complete resonating system. The
Gotcha.
whole VIC tunable card, I forgot the whole gas management connection thing that we completely rebuilt. Cherokee spent many hours on this. Many and many and many of hours. We all spent many of hours.
Indeed. I was visually tracing that freaking thing.
Yeah, I know it.
I put a huge amount of time into my version of that schematic.
Yes, you did.
All right, well, charge, baby, charge. Volts. 30 volts.
I can't remember where to hook any of this stuff back up, Sharky. I'm trying to find the darn printed circuit board layout. I found it, but I'm trying to find the layout of the components. Totally forgot. Find my own stuff again. It's pretty sad.
What's that? Sorry?
My ability to forget is awesome. Now we're still hanging in here, slowly but surely. But of course. Am I still sharing my screen with you?
No.
Oh. Turn that on in a second. See, the one reason that I really like this particular circuit is because I can adjust the voltage too, which is nice.
Oh, it's variable voltage, so you can use that as a throttling factor for the overall intensity of the VIC.
Yeah, the whole entire thing is in there.
Yeah, it's good.
Turn this back on for you. There you go. Use my other computer to browse, 'cause this thing's just too darn slow. There's everything going on.
I've got like a hydrogen oxygen incense going on here. Hopefully it's not like a whole bunch of other toxic chemicals.
From the steel, I mean.
Yeah. Ka-ching.
Did Splork show up? I just saw your announcement.
No. Yo, you got my email?
Yeah, just got it.
No, not yet, but he will. Maybe.
We'll see. It's like the Batman. It's like the bat signal for Batman.
It's like this huge knowledge base of information on my forums, and even for myself, I can't find half the things I'm looking for. I've always wanted to reorganize this thing, and it just hasn't happened yet. It's a lot of work.
No doubt about it.
Completely go through everything and reorganize it.
I'm going to make an entry on my blog real quick that some of these results are just weren't repeatable today. It's really annoying to me. I'm determined to get to the bottom of why. I hope after charging this thing for a couple hours today that it
All of a sudden works properly again. Or not properly, but works according to what I saw.
Yeah, it's repeatable results.
Repeatable results.
It's kind of cold in here today. My hands are actually very cold.
It's cold here as well.
It's very cloudy and crappy outside today.
Here too. I'll be leaving at about 5 my time today because we're going to do some Halloween stuff as a family this evening.
Oh yeah. Cool. What time is that? 5, 4, 3, 2 o'clock?
Yeah, your time too.
Okay. Who showed up? Who showed up? Nope. No plork.
No work.
whole bunch of people come showing up today. The email must have went out right away this morning.
Yeah.
Hey. Those are from the video, aren't they? That means it's before this. Da-ring, da-ring. Hi. Are you in the chat room, Alex? Jump in the chat room. There's an interesting... Sharky has an interesting question.
All right, here I come. The, let's see, open source energy chat.
That's it.
Calculate the capacity charge needed to overcome the other. Actually, yes.
I'll be right back. I'm running to the restroom.
Yeah, I actually thought about that very thing. I was looking at trying to work that out, and the geometry and the point measuring the situation in terms of point particles and the distance between them and the angles and the bonds of the water, and trying to really figure it out at that level. Like, what is the actual, what are the numbers here? So it's in my mind to work that math out. I just haven't done it yet, but I think it's a good thing that needs to be done. Like, in other words, what are the actual forces in the electrostatic field at work here, and what forces, are the forces at the level of the electrical interaction of the water molecule that's internal to itself in line in terms of order of magnitude with the forces that we can impart upon it, with a capacitor? I think that's a very important question, and it's something that I have like a few handful of calculations already scribbled down, but I don't have anything conclusive. But I think it's, like I said, I think it's an important question. It's actually pretty basic stuff too. It's just Q1, Q2. It's just a question of getting the distances and the angles. That's kind of where I am at the moment. The distances between given the angles, using the standard atomic model. Should be able to calculate those things. Agreed, Sharky. Yeah, we could. I mean, if we could hyper localize the mathematical modeling in that way, we could figure out, we could get another read on the order of magnitude of the forces involved, and that's an important check that we need to do. Like I said, I've got some math scribbled out for that, but
Plork is here. The Plork has arrived. Oh boy, we're filling up the chat quick. It must be a popular day today.
Vegator. Yeah, so Sharky, that business of amount of part molecules per per volume. I feel like we can address it as though it were a single molecule at the dead center point between the two plates. And for modeling purposes, it might be sufficient. Yes, having multiple molecules probably does provide a reinforcement, a reinforcing effect to the overall strength, but I still think the right starting point is like a theoretical single molecule at the exact 50% point between the plate distance, and then model what the math is. And then we can figure out what's the additional strength, but as a function of the reinforcing effect of the reality that it's in a material, that it's in a lattice of water molecules, not just a single one. But I feel like start off with that single one at the 50% point between the plates, and then start trying to work out the math for what's the kind of average force necessary within a given unit, area. And maybe instead of working in a millimeter squared volume, maybe we should put that down to like micron squared or something very small, and so the math becomes more manageable. But anyway, those are my thoughts, and that's definitely something we need to do.
Okay. So this one here should pulse 100K. Yellow here. And this one is here. I lost the plug now. It's yellow. black, red. That goes there. And then the switch is here. This sucker goes right here. Russ, by the way, this is Jim from the Nest Group. Oh, hi, Jim. Welcome to the live show.
Hello, Jim. Don't know you, but nice to see your words.
I can see your words. Just so you know. So I'm going to hook this up. I think I'm going to hook it up with the air cap and the original VIC coil set.
But I've been charging this now for about 45 minutes. I'm going to see what I can see. So it goes immediately to the expected 1.5 volt range. It'll sit there and discharge for quite a while like that. But I'm going to take it all apart first. Well, actually, in the first test, I let it sit there for quite a while. Maybe I'm going to do that this time. Let this discharge for quite a while. Maybe the first time. Huh. That's interesting.
Yes.
Getting an interesting little reading here in the scope this time. Well, looks like, where's that coming from? Is it coming from anything real? Yeah, it is actually. What the hell is that?
I haven't broken these cores yet, Sharky, and I don't plan on it. Oh, lawnmower time. I'm going to shut the door. It doesn't really need to be open anyway. It's cold in here today. Squeaky, squeaky, lovely door.
I was seeing an interesting waveform immediately after charging.
You always do see one?
No, actually, I never noticed it before, but immediately after charging, there was a waveform, kind of a pulsing waveform, coming from the cell itself, but now it's gone. Fix that. Hit that again.
Talkie. Fire pinto.
Temperature here is, oh, a thermometer needs a battery, huh?
It's an interesting temperature.
Yeah, really. I guess I'm going to deal with this real quick while I'm thinking about it. Volt battery. Jesus. What happened to these batteries? Like these blew up or something. Hope it didn't destroy my meter.
Oh yeah. That always happens to me. You just get some baking soda powder mix and wash it out. There's been many a times where I've completely taken a unit apart, thrown the electronics in a bath of water with mixed in baking soda.
Yeah.
Let it sit for a couple hours. Scrub it with a toothbrush. Let it dry. Put it all back together. These darn things always do that to me.
I hadn't seen that happen before. That's crazy. Wonder why it happened.
Cause it's awesome sauce. Duh.
Terrible. This is a pretty expensive piece of equipment. I don't need that going on. Freaking cell. What the hell are you doing to me?
Talking about your thermometer?
Yeah, I'm talking about a really, really nice fluke thermometer.
Oh, that one. Yeah, that's not good.
Hope it didn't like destroy it. Guess I need to take the batteries out of these things when I'm not using them for long periods of time from now on.
Yeah, that's been my routine. It's a pain in the butt, but it'll save you that trouble.
I can't believe this happened.
I can. Happens to me all the time.
Freaking battery acid ruining my equipment. And usually baking soda and water.
Baking soda and water, yeah. That eats away the battery acid.
I'm gonna get some baking soda.
It neutralizes it.
Yeah, I'm gonna go get some baking soda. Go get myself a little base on here.
Let's see, I'm gonna hook you guys back up to the top here. What? Catch up. You guys are talking to yourself. Because I'm not listening. See what this circuit's doing so I can remember what I'm doing. All right, test points. Let's see, I gotta remember what they are. Pulse indicator circuit, phase lock loop circuit, LF and E. I gotta find the full sheet. I don't know where it's at. I thought I had a full sheet of the test points. Just can't remember. Guess I can check each one. We'll find out. Take this one sheet out.
All right.
On time.
Baking sodaized it. Let's see what happens here. Hopefully it turns on still. That's really annoying. All corroded. Oh, that's good.
Oh, it's scanning.
Good, at least it still works.
Oh yeah, I know it works.
I was just worried that the battery acid got in there.
Oh, you're talking about you. Yeah, I'm listening.
Oh no, I was just saying I was worried it maybe got in there and like destroyed it, but the thermometer's still okay. So
I think that's
Good.
amplitude.
that would have been terrible. Now I can answer the question: what temperature is it? .5 degrees Celsius here. 68.5 degrees Fahrenheit. Good to know.
Melting gate time. It's pulse on time. And this one must be amplitude.
So there's that discharging waveform I was telling you. And it gets longer and longer and longer at first. And then eventually goes away. What is discharging there exactly? What is the square wave for? Where's that coming from? There it is, it's there. Eventually it just disappears. What is it doing? What is that doing? Yeah. Effect disappears at 1.2.
It just disappears?
Did you see that by chance?
No. So what exactly are you doing?
Can you see my scope?
Kind of, yeah.
Okay, so let's turn this thing on, let it charge for a minute. Got some DC going there. Now when I turn it off, there's this, there's something happening. Oh wait. I gotta, let's see. All right, Russ, real quick, I'm going to turn this off and show you what I'm talking about.
Yeah, do it.
So, see that right there? That's that square wave. It's kind of like a sawtooth wave. You see how the wavelength of it gets longer and longer and longer as its amplitude gets as amplitude goes towards, gets smaller and smaller and smaller, and at one from 1.5 or 1.6 to 1.25 volts DC, this effect remains. Once it gets about 1.25 volts DC, it just disappears.
Did you totally disconnect the power supply?
But yes, definitely.
Because I was just wondering, maybe it's the power supply.
Yeah, that was my first thought as well, but no, it's not.
Huh.
It's nothing but the cell. This is something happening inside the cell.
Maybe you should record that.
I'm going to. And it looks like what it is every here we are again at 1.24 volts, and then watch this, right around 1.2, there, gone.
You're gonna have to get a closer view. I can't see it.
Okay, I'll do that for you.
It's too far away for me to see those details.
Okay, here, I'll do that real quick for you. All right, so we're gonna turn on the power supply. Where is it? Oh.
Hold on, let me sit down and take a peek. I'm gonna eat a snack. Video time! Snack time! I'm hungry. I ain't no breakfast yet.
All right, can you see now?
Yep.
Okay. So I'm going to turn on this guy here. $30. All right, that just looks like nothing here, just DC noise. Now after I've let it charge for a moment, at 30 volts. Let me know when you're watching and I'll turn it off. Okay, so now I'm going to turn off the power supply and disconnect the leads. Okay, and now you see that waveform right there?
Yeah.
This is happening in the cell.
You've disconnected the power supply?
Yep, this is totally happening in the cell only.
Is that 60 hertz sine wave, by the way?
Nope, it's just a this is a.
It's not a sine wave, but I mean, is it 60 hertz?
No, it's not. It's some kind of square wave. It's nothing to do with ambient power. It's happening in the cell.
What if you take take it out of the water?
And it only lasts for about, yeah, I'm going to do that next. It only lasts, like, see this volt, this meter, this up here where it says 1.37 volts? When that falls to about 1.25 volts, the effect will completely disappear.
Disconnect your voltmeter then. Maybe it's your voltmeter doing it.
Well, if it is, it's be the first time I ever saw the voltmeter do that. But yeah, it's good. That's a good idea. Let's do that real quick. Okay, voltmeter totally disconnected, and the effect is still completely there. So it's nothing to do with the voltmeter.
Interesting.
So that's something actually happening in the cell. A little square, and look at that. Now it's going towards 0. See how it gets the frequency gets smaller and smaller and smaller, and then finally, right about there, it's gone. That's 1.24.
That's worth filming. That's interesting.
Yeah, and that happens every time at 1.24 volts in my cell. So 1.6 to 1.24 volts. There's a discharging period during which there's a very pronounced square wave. More almost like a sawtooth wave, but it's definitely a square wave. It's like something is discharging incrementally at a period of about 150 microseconds.
Are you connected across your cell?
Yes.
Ground lead too?
There's no ground lead. It's floating. It's just floating by itself.
Try grounding it.
All right, let me put a ground on it.
I'm going to put my earth ground back. Okay. I'm going to leave the voltmeter disconnected, because why not? And then I'm going to turn it back on. It's charging again. And let me get my ground wire here ready. Actually, let me apply the ground to the cathode, so it doesn't really do anything to the. Let's see, what can I do here? I'll put the ground. I'm gonna put the ground. Actually, ground this thing even while it's charging. Okay. Earth ground on the cathode. And I'm going to turn it off now. You ready for that?
Yeah.
Okay, so there it is. The wavelength is getting longer.
Turn the amplitude up.
It's earth grounded this time too. It's the frequency's changing, so I'm having to follow it.
Oh, turn the amplitude up.
It is interesting to note that with the earth ground, the amplitude's less high as it was before. And it's also less pronounced with the earth ground, but it's still there.
What voltages are we talking right now?
These are
It's a volt
these
and
are
a half?
about 100. It's about 100 millivolt effect. It's slowly moving towards disappearance. Whatever it is, it's happening in the water. It's happening in the cell. It's just, now we must be getting close to 1.24.
You just got one scope probe on there, right?
One scope probe not electrically connected.
Oh, you're just floating on the water.
Oh, and the fact that it's not electrically connected means it's probably not in the millivolt range either.
What if you connect it?
Yeah, well. I'm so in the habit of because I don't want the scope to be negatively or changing anything about it that I don't like to connect it electrically, but. All right, so now it's a much bigger waveform. Hold on. Now I'm in the 1 volt. All right, so I'm going to charge it. Let's see. Will that hurt my scope? No, it's 30 volt. Well, it's DC. That's okay. Should be fine. Okay, so now I'm charging. I'm electrically connected. All right, I'm going to turn it off now. Well, I'll give it another minute. All right, here we go. Ready?
Yeah.
Oh wait, I wasn't actually charging because I was disconnected. 1 second. Because I disconnected the terminals. All right, now I'm charging.
Now you can see a little waveform ripple.
Okay, disconnecting.
And there it is.
There it is. And now it's a 2 volt, you know, well, a little more than 1 volt effect.
What is it like peak?
And there, they check that out. It's a nice pronounced view of it there.
Yeah, it's like. See, is that a 60 hertz sine wave that's oscillating?
Oh, it's
those
not.
peaks?
It's nothing to do. This is very, very small.
No, I mean the frequency between the lower and the higher peak. Or is it changing too?
Well, the frequency is changing. It's getting longer and longer until at 1.24 volts, and then it goes away completely. It's not anything to do with a sine wave, with nothing to do with 60 hertz. These are very small frequency.
Yeah, but there's frequencies on top of frequencies in that.
Well, there's a peak frequency. I mean, the frequency of the peak is all I care about. The height, the amount of times that occurs.
Yeah, but that other second wave that's also in there.
Oh, that bigger one. I don't know what that is.
Frequency is that?
Let's see. Well, that's the larger view of it. There's some kind of cross-cutting frequency this thing's riding on. But that's earth grounded. Let's see if that's 60 hertz. I'm not sure what that is. Hold on. I can't get it to freeze. Hold on. There.
Set your divisions at.
That's 500. So I'm at 5 milliseconds there. If I can get it to hold. The frequency on that is 8.2 milliseconds and growing. It's changing. That peak to peak on that is
it's moving, isn't it?
Yeah. Now it's about 9 milliseconds. So it's really not 60 hertz, whatever it is,
because it's moving.
Yeah. But that's that larger one. But the smaller one, the smaller effect inside of there is now gone. I'll have to recharge to get it back, which I'll do right now.
That's pretty crazy. Interesting.
Something interesting is happening here. I think this might be important. Okay, there it is again. How is that? That's happening in the cell, and it happens only immediately following discharge.
I wonder if it's an oscillation of whatever the power supply is putting out.
Well, the power supply is not connected anymore. What it is
No, I mean like it's like a jump start. The power supply like jump starts this oscillation that the cell holds until it discharges.
Huh, that would be an interesting effect. I'm not sure what that would be. I think it's something to do with the way that the charge is. Well, let's try it outside without the water now. Let's see if it doesn't happen in the water. Because I'm curious. I feel like it's something to do with the water itself.
Yeah.
The way that the charge that's being stored in the way that the charge is being stored in the plates is discharging into the water after I turned it off. That's what I think we're seeing. I think we're seeing the step, kind of charging that happens. Electricity imparted from the plates into the water, and we're seeing the path that charge is taking through the water, but only while it's strong enough to make it across or something. So beyond below 1.24 volts, we don't see it anymore. It disappears.
Definitely interesting.
Yeah, maybe you're right, Fire Pinto. We'll see. Let's see what happens with that water. All right, so there it is. The cell is just sitting there on the bench. Now let's look at it. It's acting like an antenna. See all that radio wave signal there?
Yeah. But
All right, so
look at that oscillation still in there a little bit.
those oscillations are it's like an antenna right now, I think. I bet if I hooked up a little speaker, I'd probably hear like a Mexican radio station or something. All right, let me see if I remove the ground, if all that noise goes away. The earth ground. Yeah, it does. Yeah, see that ground, my earth ground is like a big antenna.
Oh, yeah.
And now it's gone. So I'm gonna keep the earth ground off since it makes no difference. It actually it's just adding EM that I don't want, so. All right, so, all right, here we go. I'm gonna charge it back up. No water here. Now I'm gonna turn it off. That effect is nowhere to be found anymore. This is the effect of the water.
That's rather interesting.
So we are actually seeing the path of charge from the plates, the charge stored by the plates, down to 1.24 volts. It's sufficient enough to perpetuate an EMF of some kind through the water that has a 150 microsecond frequency, discharge frequency, and that's something to do with the water itself, because that effect doesn't happen in air. Let's put this back in the water now, and see if let's see if just by putting it in the water it just resumes. The effect is suddenly visible. All right, I'm going to turn it. Let's see. Put it back in the water and try again. Okay, that peak to peak that we saw before.
Yeah.
Was the earth ground. Now, because I can get rid of that by removing the earth ground.
Oh,
See that
extra peak?
Yeah, that's coming from noise from my earth ground, which is connected to my.
I don't see anything because I'm on the bench.
Oh, sorry. That peak to peak here's the earth ground. That peak to peak comes from the earth ground. You see that?
Yes.
Removing the earth ground. Gone.
Okay. All right. So that's where that came from. That's good to know.
Yeah.
So.
Charging. I'm gonna give it a little time to charge here. I took it all apart. Okay, look at that, man. Look at that.
Oh yeah.
And the frequencies are getting bigger and bigger and bigger. That's amazing.
Is that?
I think that's amazing. That's an effect of the water.
Well, I have a question though.
Look at that. Look at that.
Get your camera on a tripod or something and let it sit stable.
That is awesome.
Sauce.
That is really, I mean, I find that to be pretty exciting. I know I'm a nerd.
It's okay. It's interesting for sure. Yeah, that's
This
good.
is an
Right? That's
effect-
good right there. Leave it right there. I'll turn it back a tiny bit. There you go. So do me a favor. Go get a different jar.
A what?
A different jar. I want
That's
to
a
see.
503 microsecond frequency there at 400 millivolts.
What happens if you short the cell out?
Let's see. Effect is gone. And now it's permanently gone. That's awesome.
Charge it again. Do it shorter. Just barely charge it. Just for
I'm going to do it again at 30 volts for like 5 seconds.
No, do it even less. Do it like just a blunt.
Well, there's 30 volts for 2 seconds. I don't see it at all right now.
No, do it
It needs to be
again.
charged a little longer. Let's do 30 volts for 10 seconds. And by the way, my scope probe is on the cathode. Let me put one on the anode too.
You got one probe on each side?
Yeah. All right, turning it off. Boom, look at that. The cathode, look what the cathode's doing.
Are you saying the cathode is the inside or the outside right now?
Inside. Only the cathode, the anode's not doing it. Which means the charge isn't going, it means it's happening near the effect is happening on the water near the cathode, I would say. Let's see if I can get anything by going deeper or closer on the anode. Look at that.
It's like it's a charge discharge. It's like a discharge
it's like
curve.
it's discharging. Yeah, I mean it's just
what's charging it? What's the little peak?
it's the plates imparting charge.
So I want you to do me a favor. I want you to put that in a totally different jar. Go get a masonry jar or something with a different shape. And see if the shape of the jar is making it happen.
I think we'll find that it doesn't, but let me see what I can find. And look at, I love how the frequency just kind of, the overall frequency grows over time.
Yeah, so I want to see it quit here. I want to see it go down to nothing in a minute, which is
And
interesting.
it's fascinating to me that none of this that this doesn't happen on the anode at all. And look at that. Now it's getting ready to blip out. Look. The end of the effect right there.
that is totally interesting.
That is so freaking cool, man.
Yeah, we definitely captured some interesting stuff right there. That is definitely odd.
That is so cool. I really, really want to understand exactly what this is. I think it's important. Okay, let me find a different vessel for you.
Yeah, I just have a curiosity because your vessel is kind of spherical shaped.
Yeah, I know,
So-
I know what you're thinking. This cylindrical vessel right here. Oh, you can't see it. But I'm going to use this cylindrical vessel.
Wait,
I'm going to go
tell-
wash it out first, though.
Hold on, before we do anything, I'm gonna connect this little single lonely cell the same way you have yours set up. So how do you have yours connected exactly? Where's your ground at?
I actually took the ground off because it just adds noise. It's just
The ground on your scope is disconnected.
the ground on my scope is well, okay, yeah. So I've got an earth ground that's just always in my lab. So and that's common to everything on my bench. Except sometimes I run an earth ground just out to the plumbing system of my community as another earth ground for tests because I find it useful to have a different ground. I can see it gives me I notice that it gives me different results than if I'm using a common ground everywhere on my equipment, and then if that ground's common to my experiment, it's like I don't see any difference at all. So to answer your question, there's an earth ground on my rail to my wall. Like there's all my equipment, everything, this whole garage has got an earth ground on the negative side.
Here, I'm gonna hook up. I've got both of my scopes on each side of my cell.
Okay. See if it looks like mine.
And there I just hooked up one voltage source on one side of the cell. So there's the other voltage source on the other side of the cell. Oops, let me change the probe setting. So how close are you in? What's your range on your...
200 microseconds per division and 200 millivolts. And I'm electrically connecting my scope right now.
200 US?
But yeah, US.
And what's your scope?
Time division 200 millivolts.
Okay, I'm actually can't get there. I'm gonna have to do 500 for the moment.
Okay.
Ooh, I'm making gas though. Lots of gas. I don't have distilled in this particular cell, but let's see what happens when I disconnect it.
Yeah, I'd like to see if I can get the same result with other kinds of, I bet I won't get it with tap, honestly. I think this is discharge because of the high resistance of the distilled.
Got some noise there, but...
And there's that same peak-to-peak I had. You had something similar a second ago.
Yeah, and there's like this oscillation in there.
Yeah, that's the same one. That's the same form. That's your ground. Take your earth ground off.
I can't. Oh, I can. Let me break the back of my probe scope off. Hold on. Actually, that's probably not grounded either. Hold on a sec.
Just let it float.
I've been wanting to do this for a while, so I'm just going to do it right now.
I tell you, that N50 I put on my winding setup, that thing is freaking on there. I was trying to take it off last night. And I don't think I'm going to be able to get that off.
What did you do?
I remember I told you about that N50 on the different components of my winder. And I put it on a solid slab of iron that is my table saw.
Oh, yeah, that's right. Your magnet. That's right. That's right.
Never coming off of there.
Okay, I have no ground anymore. It's gone.
Oh, but still you have more noise.
I'm at 1 volt.
You got a 1 volt of noise. With the ground you were better off, huh?
Well, check this out. I'm on a 100 millivolt scale on that blue.
Yeah.
And 1 volt on the... Oh, here it's on times 10. There we go. That's why. Alright, let me charge it back up real quick. Got this oscillation going.
I'm gonna try it with let me just see. I'm gonna try it once more with a lower volt. I'm gonna start off with 12 volts though.
Okay, I'm gonna hook it up to the other cell that's distilled.
See if I can get the same effect at 12 volts. Okay, it's charging. Charging. Stop charging. There it is. I need to think about what that waveform is telling me. It's not telling me anything right off the top of my head. It's weird. I can't understand what the source of that charge is, other than it has to be the capacitor plate itself. The capacitor, the plate of the capacitor is sending a. What's the frequency of it is? Let's see. It's 600 millivolts, and it likes this 503 microsecond frequency is where it wants to stay for quite a while. The frequency gets shorter and shorter. 465. I'm gonna plot those the frequency over time, and now look at it. It's getting, the amplitude's getting smaller, and now it's going in for death. Frequency is going smaller.
That's crazy.
That effect is gone.
That's crazy that you can't see it at all on your other probe. Switch the probes around.
Yeah, the other probe, it's just happening on the cathode only. It's happening in the source of charge. Which means the effect isn't getting all the way across the water. It's only happening locally at the source of charge. If you follow me.
Yeah, I'm following.
I just reversed the probes. I'm going to shut my garage door because of the lawnmower.
Yep. I can't hear it right now, though.
It's so freaking loud.
I know. Alex out here is mowing this yard, too. Little bit of yards there is.
All right, so now we got a switch. I'm going to charge it up at 12 volts. Oh, that's not working because I got to reconnect the power. Okay, here we go. Charging up at 12 volts. A little while, for a moment. Okay, now you should see it on the same effect we should see on the top probe. We don't, though.
Hook both your probes up to the same side. See if you see it. On one and not the other.
Yeah, okay, hold on, let me make that happen. Oh, you know why we didn't see it? Because I didn't disconnect the power supply here. That's why we didn't see it. You don't see it if the power supply is connected, actually.
I can't seem to find what you have there, but that's okay too.
And I know why we didn't see it. It's because I left the power supply connected. You only see it if you disconnect the power supply. Because otherwise the power supply overwhelms the effect somehow. Okay, so we're gonna do it again. This time I won't forget to disconnect the power supply. Here we go. Charging. Fine tuning to 12.1 volts. I like it there. Disconnecting. Boom. Now it's on the top as we thought it would be.
There you go. So that confirms it's not your scope or something.
Yeah.
Which is good.
I just love this effect.
Did you get a different vessel? Because I really am curious.
I do have a different vessel, but I need to go wash it. And then rinse it with distilled.
Yeah, because I really want to see what happens in that.
That is a beautiful, beautiful effect right there. I'm just going to watch it discharge, and then I'll go. This happens on the source of charge. This is local interaction between the cathode's pressure and the water. And we're seeing discharge. We're seeing 400 millivolt discharge. This is something to do with the molecular nature of water. And as it discharges, the amplitude gets smaller. As the charge pressure on the plate grows smaller, the frequency of this effect gets smaller, as does the amplitude. Higher frequency, more pressure. There it goes. It's disappearing. Gone. Higher frequency, more pressure, higher frequency. Wait. Lower pressure, higher frequency. Lower pressure, higher pressure, lower frequency. That's weird. Higher pressure, lower frequency. What about water would respond in that way? Higher the pressure, lower frequency.
I think I have an idea as to why that would be. But I need to experiment with something first to figure it before I'm ready to say it. Okay, so now we should do a video. Can you turn on the video apparatus?
Video apparatus has been recording. It's all done. But
I just mean we should
but-
make a video and
Well, we don't know enough about the effect yet. Once we polish, in a week when we polish this up and really understand it, then we'll talk about what we think we're seeing.
yeah, we can publish an actual video, but this one will still be on there for people to chew on. Not that many people go and watch these videos, the live recordings, so.
Yeah. I'm gonna do another test just because I want to. Let's try something here. Then I'll go wash out my other container for you.
Can't get my frequency selector to change its output here. I gotta figure out why.
There it is. Thing of beauty.
That's cool.
What the hell is it doing? Why? Okay, so 200. As the pressure goes smaller, the wavelength gets longer. Higher pressure, lower frequency. Higher pressure, lower frequency. It happens less often the higher pressure. Happens more often when the pressure's high, which actually makes sense if it's dependent on some condition of the water molecule. Okay, so as the field relaxes, as the polarity, the general polarity relaxes near the cathode, the frequency of this discharging happens less often. There it goes. Goodbye effect. And that corresponds to a charge pressure of about 1.25 volts. This happens during the during the range, the voltage pressure range of 1.6 volts to 1.24 volts DC. Are you still working to get that going over there?
Yeah, but I'm listening.
Or did you change gears?
No, I'm still working on getting this working. It
Gotcha.
works, but the primary's pulling a lot of current, so I'm making some adjustments, but I'm still not understanding why my frequency adjustment's not working.
Did you try DC? Did you just try this test with DC? I just want to make sure you can repeat it.
Oh, what test with DC do you want me to try? I didn't see anything. Then again, I got a different scope.
Well, it should still. I mean, it should still. You should still be able to see it with the scope.
What do you want me to do?
If you just apply 12 volts DC, and then disconnect your power supply.
Yeah, I did all that.
And then let's see if we get a result.
I didn't get nothing. I didn't get nothing. It's just noise.
All right, so let's tune you for zero noise at the start. What I've got is,
when I hook up my earth ground, the noise gets better.
Okay, so let's do that. Because I can hook mine up. It actually makes it worse in my case, but...
do you have just a regular wall you can plug your oscilloscope into? Like no grounding?
It is not grounded.
Okay.
I mean, I don't have an isolation transformer, so I don't know if neutral's grounded internally, but...
Okay, that's fine. And then, you do have an earth ground, though, that you're adding, and that makes things quieter, which is good, which is what you'd expect. In my case, I think my earth ground is just acting like some kind of antenna. Remember I told you when I use the extension cord, it really acts like an antenna and brings a lot of noise, but if I use a thin gauge wire, it's nice and quiet. Right now I'm using an extension cord, and that's probably where all my noise is coming from.
Okay. So look, I'm going to apply with distilled water.
That's just DC right there? What's your time scale?
12 volt. There's, wait, where were you at, 500?
200, I'm at 200 millivolts and 200 microsecond US.
Well, there's 500 millivolt. I can't go any lower or else I can't see it on the screen.
Can you go to 200 and just move the line? Do you have a position adjuster?
I can only go so far.
Okay. So that's fine at 500. I'll set mine to 500 too. Hold on. Now I'm at 500 as well.
Okay, so this is what I see, okay?
Okay. So that's fine. I've got a nice steady, and you got some oscillation. That's okay. We should still see it. So now apply 12 volts. I'm going to do the same.
No, I'm applying 12 volts.
Okay, so now I'm applying 12 volts. When I apply 12 volts, I see a lot of stuff happening just like you as well, but I see it in an analog way. So now at the same in the same motion, turn off your power supply and then disconnect the negative lead from it. Well, both leads really, but at least the negative lead.
Okay, they're both disconnected. They went off screen.
So what do you see?
Nothing. The same ripple I had whenever I didn't have anything hooked up. See, if I go to 100 millivolt, like this. They both have the same oscillation. It's exactly the same. There's no different between them. See all this noise?
Yeah, okay. I wonder why. What the heck is the difference?
I probably just darn digital scope, man.
That's true. I have a pretty high-end scope. I mean, this thing was extremely expensive when it was new. I don't know though. Yours is nice too, so I'm not sure. Hold on a minute.
I cannot achieve what you're achieving, but I don't have the same scope. That guy backed out on me.
Well, let me see if it happens with the other power supply.
Yeah, that's what I was thinking too. So I wonder if that thing's putting out an oscillation of some kind that's helping that thing resonate internally.
Let's find out, because it is a really weird waveform. Very hard to understand. Oh, look at that. Okay, so now when I put it in the other scope, I get this weird thing.
When you
I mean, the other power supply. I mean, I don't know what that's about.
That's with it on?
No, it's not on. It's about to be on though. Okay, so voltage. Ooh. What is that about? So here's the voltage with what the heck is that? So I'm going to keep it at 500 volts, but I'm getting this big waveform. Let me just change this real quick so I can see what that is. Okay, that's just at 10 volts. I can see that it's just 60 hertz happening there.
Yep.
So I'm not worried about that. I'm going to set it back to 500. Now I'm going to jack it up. Current. So I'm going to take it up to, I don't know, 50 volts or so, and then turn it off and see what we get. All right, so I'm at 50 volts. Now I'm going to turn it off. Now I got this. So that's a different waveform. I mean, it's similar, but different. It's like the water remembers the sine wave or something. What?
It's what it appears. Like it's actually, you got it totally disconnected.
You have to disconnect it, yeah. But then look at that. Now the sine wave is still being remembered. I don't understand that at all. The effect is still happening in there, and it's still like, see how it's still slowly just still happening, but it's like the water remembered that sine wave too. Look at that. What in God's name is that? And it's opposite polarity now too.
Yeah, it flipped. Zoom so you can see the sine wave a little bit better.
That is so weird. I just changed the wrong knob. Hold on. So now the sine wave is in the water. What were we saying? What is that? Why is the sine wave in the water?
Well, it's not opposite now.
It's the opposite. Those are one on
Now
each
they are.
one on each side. But now look how the polarity is shifting. It's like the one on the bottom. It's like phase shifting a little bit.
And it's got this peak at the tip.
is
Something
really-
in your laboratory's messed up, man. What is going on over there?
Yeah, I don't know.
What if you charge it with a DC battery?
Okay, let's do it.
It should just stay DC. I wonder if the something smells hot over here. Maybe it's just me. I wonder if
Okay, I'm gonna do it with the battery right now. Okay, here we go. So we're at 11.34 volts. The water still seems to remember that waveform, I guess. I mean, it was flatlined before, so maybe I should put the ground back on it. Anyway,
you got
now I'm taking it off. Now I got those things are happening in there. The discharge pattern's still happening in there, but it's riding that wave. It's riding that. But the other power supply like neutralizes that larger waveform.
Wait, just for fun, hook up the other power supply.
And see if I can make it like remember the.
Yeah.
It's like it's yeah. Okay, so now I'm going to connect the other power. Just connect it to the. Whoa. Other power supply is not even on. And it's totally flatlined. Turning on this power supply. Charging. 12 volts. Now removing the terminals.
There you go.
I can't understand it.
I mean, to remember, the water's remembering what you're telling it, which totally makes perfectly good sense to me.
It's an interesting way to think about things, and it does seem to be what we're seeing.
That matches some of the understandings that I have.
Water likes to remember what you tell it. Maybe that's why we're made out of it.
No, I mean, it really does. Like, if you have new water that's not really been structured much, then that's some of the results you can see.
It's like you can just impress whatever you impress on it, it just remembers it.
If it's clean, fresh stuff, yeah. Like I don't have a problem with that answer. That works good for me.
I like it too.
I mean, it even makes sense out of all the stuff I know about it.
I just want to know though, how do these measurements impact our goal? You know. Look, there it goes. Bye bye.
Hey, how long?
And it's by the way, it's doing that even on the battery, even on the other power supply. It's just doing it riding that amplitude modulated wave. You know?
Yeah.
It's still doing the same
What if
time.
what if you reverse the polarity on the cell? Let's make the outside positive.
I hesitate to do that because I noticed, you know, well, let's do it. Because I noticed, like, you know how this electrically neutral one that I have?
Yeah.
I just feel like I don't want to confuse the atoms of my plate. Because then I might start getting really unpredictable results.
Yeah, I know what you mean.
I need to make a third identical. That's what I'll do.
Do you have enough?
It won't be exactly identical because they sent me one that was a little longer. But the cathode's a little longer. But I can do it with it. It's pretty close, but These other two are almost exactly identical within very high tolerance. This other cathode's a little, longer within the hundredths, or the tenths rather. Earth ground. Let me see something with the battery and the earth ground. That's just the strangest and coolest result.
That's definitely an interesting result, that's for sure.
Okay, doing it with just the battery and an earth ground. Oh wait, did I disconnect my earth ground? Let me go double check. No, I'm still alive out there, okay. So that earth ground's got that radio signal stuff going on, but it's all right. Okay, going off the battery. Charging up. Charging the water with Mexican radio station and 11 volts. Let's see if the water starts singing back to me in Spanish.
That would be pretty awesome, actually.
That would be.
That'd be something to see.
Okay, taking it all off. Now the top plate is demonstrating that effect more than the bottom one. It's all modulated heavily by the radio station, but yeah, it's too noisy to really see. I need to get a cleaner earth ground. I need to stop using the extension cord because it's too much of a radio antenna. I gotta go run some 28 AWG.
Okay.
Or just disconnect this. I guess I'd rather deal with the 60 hertz than the complex radio frequencies. And now, but let's see, the water doesn't seem to be remembering all the radio frequency stuff, does it?
No, it doesn't seem to. It might, we just don't notice it yet.
Well, there's that discharge effect. It's definitely, it's definitely happening. Now it's happening on both sides, though. With opposite polarity.
Looks like it has that other sine wave in there, too.
It does.
What'd you do different?
I'm not using anything except the battery.
Oh, really?
There's nothing. Yeah.
You're using a DC battery power supply?
Just the battery.
What voltage? 12 volts?
11. It's because it's somewhat discharged. 11.3. Boom. Now look at that. The cathode is on the bottom. The anode's on the top. The frequency on the anode is about twice. Opposite polarity and about twice the frequency of the cathode. It's the weirdest freaking thing. I need to go get a good earth ground so I can look at this thing. There's something weird. When I do it with my switching power supply, everything's flatlined. What the hell is that about?
Yeah, when you just hooked it up.
Like if I plug this into my, let's see, if I just plug in the anode, look at that. There it is. If I plug in just the cathode, with that. What? But if I charge it that way and then pull them both out, then it stays clean. I don't understand it. What's going on? All right, I'm going to go make a clean earth ground so I can try to see that without ever touching this one supply.
Okay.
It's a little less noisy. A little.
Okay, Shubis. Reload port 2.0.
need to get that flat line.
Oh. This is Alex. Hello, this is Alex. Hello? Hello? Who's going there? Is anyone there? This is Peter Frank called. What? I'm not sure why they called, but they can leave me a voicemail. Oh, what is it? What is that?
Well, I'm gonna try one last test on this thing, and then I'm gonna spend some time thinking about what it could be that we're seeing. Not today, but later, and then I'm gonna start moving on. I'm gonna start doing some coil stuff after that.
Okay.
I'm gonna think about this kind of offline, like I don't understand what it could be. That weirdness about the sine wave. Oh, that's just so weird to me. You really think the water can remember?
Yeah.
Like it's like a recording medium for EM signals?
Yep. I do.
It's a pretty interesting property of water.
I think about it all the time.
Huh?
I think about it all the time.
What's that noise? Is that your device?
Probably.
What's the context in which you think about it?
So you can program water to remember anything you wish. So
I know you can do that with RNA, but I've never done it with water. Well, I guess I just did, but I didn't realize that was going to happen.
yeah, like it's interesting that yours is like discharging though, and showing that discharge, but like the oscillation that was in there,
Yeah.
that kind of makes sense to me. Because I know you can program water down to that level,
Yeah.
but what you're showing is a little different, I guess, than what we would standardly think of.
Right. Well, I need to figure it out.
Yes. I'll be right back. I'm gonna rinse my cup out and get some water.
Okay.
Do you have a variac or an AC supply?
I have AC supply. My AC stuff isn't hooked up right now. What I usually do is run a signal generator through a board, and then run that through like several thousand watt power amps used for audio. So within lower frequency, I can do all kinds of craziness, but not up through like really high frequency. Just up to like about 20, or actually up to about 30 kilohertz.
Well, how much current does your frequency generator put out? How much voltage?
Well, the frequency generator puts out up to 10 volts, but but if I want to put power behind it, I run it through the power amp and everything.
Because what if you just hooked your signal generator up to that thing at 10 volts and set it at a frequency and see if it holds it?
All right, let's see.
Even though it's not much current, it doesn't really need to be, I don't think.
Let's see what we get. Christ. Go ahead.
Like I'm getting sick.
Oh no. We're going over to teacher time?
So unless Kirby really is legit sick, then I'll just take killing him and you'll stay here with. Or you could take like around.
Either way.
Alright, we'll see on the plate. I just thought Kelly might want to see those kids, you know?
Yeah, he probably would. I'd like him to as well.
That's the whole reason I'm doing it.
Yeah, I figured. Tell you one thing, that whatever you're doing over there sounds really cool.
What's it sound like?
It just sounds like some kind of really high pitch, like wee, and then woo.
That's the resonant scanning circuit you hear. It's scanning
Yeah.
for a frequency.
Right, it's trying to lock in, huh?
It's trying, but I think I need to figure out a few more things. I'm trying to figure out if my 5-volt, my power regulator is not working right. So my voltage control, trying to figure out why. I figured out why my frequency wouldn't work right, but the frequency range of which it's scanning is, I think, too low for my setup. I always found resonance at a higher peak, but it's interesting though that Don was saying when he said it would scan, it would lock into like the third harmonic or whatever, where it wouldn't be the full resonance. You know, it'd be like 3 peaks and then.
Yeah.
And so I wonder if that's on purpose. Like it just has to lock into a harmonic. It doesn't have to be the perfect resonant frequency, and it will still function. I wonder if that's why, because this is too low of a frequency. For all the coils that I made, none of them have resonated at this low of a frequency at the voltages that I could achieve from the higher ones. It's, you know what I mean, like.
Yeah, the stuff I'm engineering right now for the VIC is I want my it's all going to be resonant frequency at 1,000 hertz.
Yeah.
Or in that ballpark.
Yeah.
So we can test those ideas you're talking about with that in mind.
You got your signal generator hooked up to it?
I do, yeah. See, I'm getting an oscillator. Huh?
Put in like 150, or I mean a higher frequency, like 1500 hertz, 1.5K. Like, see if it will.
Right
trigger.
now I'm at 1K right now, so I'm gonna go up to 1.5K.
Where did my waveform go? What?
You have to zoom in to see it. There you go.
No, I just turned off the waveform. It's completely off. I don't
Oh.
understand why. All right, so in phase on both sides of the cell. It's at 8 volts. There's some kind of phasing going on, but that's probably, let's see, what? Well, let's just turn it off now and see if anything weird happens.
I don't think it will.
Yeah, it's just gone. Actually, that's 200 millivolt view. I'm supposed to be putting out 8 volts right now. What's that about? Let me see.
Maybe your resistance drop across your water.
Maybe, but where's my? Oh, my scope probe isn't connected. That's why.
That will do it. All right, so this is the cathode side. The anode side. Whoa. That's really looking weird. That's a pretty cool waveform.
Oh yeah.
So that's a 5-volt. That's definitely the waveform. So why am I seeing nothing on the 1 volts?
I guess nothing's getting across the water because let's see, what's going on here?
It seems to be disconnected. Let me verify that. Oh. What? Interesting.
Oh, it's working.
Is it locking in?
Voltage control is now working. I had the pins connected wrong, which I knew that. I just didn't know how they were supposed to be, but I got it. Oh man, these schematics are old. This is dated 2012. In February we was working on this. It still works. Alright, so I'm all connected correctly. Now I'm going to hook up my primary directly. Now I've got voltage control. I've got frequency adjust. Put them on 1 amp meter.
What?
This, can you see my screen? See the blue peaks?
I'm looking 1 second here. Okay, yeah, I do.
All right, the blue is my detection circuit saying it's detecting a peak at which it wants to try to lock onto. It's just scatter blasted.
Let's see, yeah.
It's so confused. It has no idea what it's doing. It's trying to lock onto like all sorts of stuff. But it doesn't though. It doesn't stay there. It has to stay there for a certain amount of time to actually truly lock.
Right. Well, so the amplitude across the water is slightly phase shifted, but it doesn't remember anything. It just does flat as soon as it's done. So I don't know. I think you need power to make it remember stuff.
Oh, right, yeah. Well, because it has to charge up to that potential.
Yeah.
What if you charge it up with a DC power supply and then turn on your signal generator
I could do that real quick.
to see if it's holding a potential? It just needs a little bit of oscillation to get it
A little
going.
guidance. Yeah. This is a job for my power amp. Although I've done a ton of that with power amps and I never saw anything weird. So probably we won't see anything, but I'll set all that up. But just not right now. I want to get to my big stuff.
Yep.
Well, this was kind of interesting. I spent more time on this than I planned, but that one effect was very interesting.
Absolutely.
The discharging effect of the water, yeah. I don't think I'd noticed that before somehow. I don't know how I didn't notice it before.
Try this one more time just to see. Still does it. Wow. That is an interesting effect. Play with it more later.
Did you get a different jar yet?
Oh no, I didn't. I can do that real quick. Let me do it.
You should definitely just try that one at least before you stop, because that's an interesting thought.
I'll try that for you, sure. I'm going to use this bad boy right here for you.
Oh, pretty.
Why don't you go wash it first? Okay, here we go.
Okay.
That circuit is very cool sounding.
Well, I think you can hear it more than I can because it's not that loud over here. It's very kind of quiet, really.
It makes a good amount of noise. The frequencies are getting picked up really well by your mic.
For some reason. All right, so I got it now in this larger vessel, cylindrically shaped.
Okay.
And I'm going to pour some distilled in there. Quite a bit of it, I would imagine.
So new water.
New water. And let's charge it up. Right. $12 volts, no current. Oh, I need to put the scope probes on it.
Well, you know, if you want to see anything, yes.
Yeah, exactly. Okay. Okay, disconnecting. Same effect.
Yeah? So how about tap water?
See, I just want to watch it disappear. It usually starts getting shorter and shorter as the amplitude gets lower and lower. There it goes. Goodbye. Jack it up a little bit. Okay. There it goes. Go on. Now with the battery. Now with the battery, you see it on both sides. Once again.
Like before.
Yep. That is a mystery.
That is really odd that it would introduce a sine wave like that on both, and just to see it on both sides.
And it's just the same. It's still what's going out though, like you see. It's just slowly getting ready to completely disappear. Gone. Test.
But the sine wave is still there.
Sine wave's still there though, yeah. In fact, this looks like a ground. I mean, it's not connected to anything, but it looks like that ground. It's just moving through the house, I guess. All right. Well, you want to try tap water real quick?
It's up to you. If you want to do it
Probably,
later.
we'll probably see it still in tap water too. Well, the tap water is a much better. Tap water gives me a capacitor that's like in the microfarad range, which means I don't know. Let's see what it means. I'll go do it.
Dump your 20 cents worth of water down the drain.
Well, it is after all only 20 cents worth of water. It's worth it. It's in the name of science.
That's right.
We're working with big budgets here. I can drop 20 cents.
My Wi-Fi quit altogether today on me. That's not happened. Oh well. Well, I got the circuit hooked up. It doesn't do what I want, so I'm going to take it back apart. Put it back in the box. I accomplished my goal for today. Now I'm gonna.
Hey, you got to send me that printed board. I really want one of those cool sounding circuits.
I got one for you. I'll send it to you. I can crank up the.
It'd be nice to, because I built circuits to do similar, but it's on the breadboard. Once I take them apart, they're gone. And I got to build them again. It'd be kind of cool to have something I can pull off the shelf like that.
Exactly.
I decided a while back that I'm not going to be doing a lot of, scanning and things until I see the basic EPP.
Well, that's it. I just wanted to break this out and see if it would lock into what I wanted it to, and well, it didn't. So that's why I said, okay, got it out, it worked, and I'm done.
Yep. Red.
But that's okay.
I think the effect will work just fine, or at least it'll be visible just with a single frequency that's not riding around too much. Yes, it'll be optimized with that, is my belief. But I think we can still see EPP going without just static,
Well, the thing is
I know about the bubbles idea, but still, I think it'll still work even with the bubbles.
yeah, I don't know if this was designed originally from Stan's perspective or his brother's. I don't know if it was really like, hey, we can do this manually, or we can build this really, not overly complicated circuit to just scan it and lock in for us. What,
right.
What do you want to do? Well, all right, sounds good to me, and done. So I wonder if that was kind of the case, like if that was.
Right. To what degree, like the real-time nature of it is crucial. And obviously, it's a good thing. It's necessary for a reduction system, no doubt. But
for right this moment, for us, no. But I did want to see if it would lock onto anything. And I remember I played with Tony's. Tony built, he designed his version. I played with it for a while, and it would lock on, but it would lock on in random stuff. It wouldn't work the way it was supposed to be. Now, if I may set this up another day.
Well, it's a little bit of noise right now. Hold on. I'll meet you for a second. I'll be right back.
Okay.
All right, I'm back. I'm going to real quick do a test with just air again,
Okay.
just to confirm the results. It's good that you're here to see these results because I hate for it to be like the next time we look at it, it just doesn't, it's not there at all. And then I'm like kind of like with the results that I had this morning. I'm glad you're seeing it too.
Yeah, and it's being recorded,
Yeah.
actually. So it's...
I wish I'd recorded those last time. I gotta just start recording everything. It's, as you know, sometimes it's just tiring, the thought of pulling the video camera out and editing everything.
You have no idea.
Yeah,
You just told me sometimes you don't even like thinking about it. Yeah, well...
Right, you're always doing it. It's
I'm
like,
constantly doing it. I don't even have to think about not doing it. I'm like, man, it would be nice, but it is fun. I enjoy doing it, but it is... I have so much footage right now that it's going to take me a week straight of editing just to get it all put together. And I can make 8 videos.
Yeah, I mean, and the reality is, there's probably only a small amount of it that's interesting enough to be in its own video.
Right. I could have made individual videos, which I was going to do, and then I decided just to make it all in one, but then it's going to be like a much longer video than what I would normally want.
Right.
So it's hard to be detailed and cram it all in there at one time.
All right, here goes the test with just air, just to sanity check everything here. 30 volts, just charged up. Everything's good. Okay, turning it off. Hey, look at that. The effect is there in the air for much less time.
Oh, but you still see it?
Only for a moment, but it might be because the water is on the bottom of this thing.
I was going to say, you still have some water in there maybe.
Yeah, I do. Before, the last time I did that test, there was no water whatsoever. Yeah, there's a pool of water it was in. That's got to be the difference. Let me dry that up and see if I can make it go away. It was very, very brief, but it was there for a moment.
We'll be on for another...
What?
2 hours at least.
Say it again?
Electro was asking how long we'll be on. I said probably another 2 hours at least.
Yeah. Okay, so there, I'm going to try it again dry this time. Hopefully, I think it's more dry.
I'm going to hook up
right there, but we'll see. 30 volts. Okay, pulling it out. No. Now that it's totally dry, the effect is gone.
So, it is the water, but I'm curious if you use another substance. Like, I wouldn't do it now, but sometime write down to try it with some other substance to see if, you know, like, I don't know. Throw in hydrogen peroxide in there for sure. Just whatever you got laying around the house that's liquid that won't destroy anything.
Well, hydrogen peroxide is practically water, just a little extra oxygen. Oh yeah, getting the torch shield there.
Alright, that's back to where it used to be. Now I want to try something. I want to do... amps.
Alright, so trying tap water just to see. That'll be my last test on this for the day.
Okay. Alright, I'm going to get a little more scientific for this test today. Do a little more calculations here. So what I'm going to do is I'm going to say 0.01 amp at 30 volts DC. Alright. I'm going to let this sit.
All right, let's try it. It's with this tap water.
And do this one.
Oh, interesting.
What? It already has memory?
Oh well, okay. I was like, it's going crazy over here with the gas production. I'm like, oh yeah, right, because it's just it's tap water at 30, you know, it's at 30 volts. Okay. And that effect is not there.
You don't see it at all?
Not really. I think it requires the distill. Well, let me see here. Oh, it's there. It's just not as the amplitude is much smaller.
Maybe it's only the pure, like it is truly the purity, like the water itself is the thing that's making it happen.
Yeah, and because of the higher resistance, you get a higher amplitude of the effect. It's pretty. Oh, and that was it. I'm getting a weird periodic harmonic of some kind. See that? What is that?
I don't see that. It's too far away, but it's okay.
Let's see if I can back out. You know, the effect is lasting a lot longer though with this.
Really?
I think it is. I think because it's a higher capacitance, so the charge holds longer. Because it's a microfarad capacitance now. The cell overall is going to hold its charge for a longer period of time. It's going so that's kind of expected. It's going slower. That's going to be because the capacitor is discharging more slowly. But it's heading. It's almost out. It's almost out now. It's on its way out. So higher peaks with tap. I mean, lower peaks with tap and slower dissipation of the effect. I'm sorry, lower peaks and slower dissipation. And with distilled, it's higher peaks and faster dissipation. And with air, it's zero effect. And with a tiny bit of water, it's very fast dissipation of the effect. And high peaks. With very little bit of with distilled, that is. All right. Well, that's all recorded.
Yes, it is. On your camera, you mean, or this one?
On the Gries Petty Research monitoring camera.
Gotcha. All right, so here's what I did. Oh man. Oh yeah, that's okay.
And the shape of the vessel seems to make very little, if any, difference.
Good. I'm glad that you confirmed that. I got a restroom break. I'll be right back.
Okay.
Oh. Getting the roots of my teeth scream. That sounds awesome. Ouch. 5 hours, yeah. We'll be done probably before you're gone. Before you have to leave, I should say. Alright, so where is my... Let's see, I'll take this out of here. Put it in here. Plug in some numbers and do some math.
Coca-Cola.
So I'm going to set up I'm going to do some calculations and set up my test today with the VIC under slightly different math than I'm usually trying to make it work. I'm changing the resistance of water. I'm going to try to impedance match using the true value versus the resistance of water that we always kind of were contemplating back and forth what we should use.
You're talking about the 78 thing?
Yeah, so I'm actually plugging in a real test value.
That's what you should do, in my opinion.
I know, and
Yep.
I haven't necessarily tried that yet, and so that's currently I'm going to try that I think today.
Good.
Now that I know my other circuit works exactly as it doesn't. And I figured I did learn something though today, that the amplitude of the feedback signal affects dramatically where it finds its resonant circuit portion, for where it tries to tune into. If that
Well, that's
makes
good. Every
any
test
sense
is
at all.
valuable. I learned that this effect in the water is very, very interesting today.
That what you got going on over there on your bench is very interesting. I would like to see you have exact same results with something else. I wish I had a different scope. I think this digital scope is a good tool, but an analog scope would be nice to back up its validity.
Yeah, and to your point, I'd love to get a digital scope as well for the same reason, to kind of have that full range of capability.
I'm still looking. I am going to buy one on eBay of your type. I just got to find another one. I just didn't look yet.
Yeah.
Oh, did you see that file I posted with all those measurements?
I did. I looked through that. It was very cool. A lot of good work in there.
Yeah, that's like years of work. But that very last portion is those new coils, and they match almost exactly.
Well, I'm still kind of figuring out what I'm going to be winding, because I'm really trying to get. I'm going to have a very unusually high step up first of all, and I'm going to have a very low resonant frequency. That's what I'm working on over here, and trying to make sure that my calculations are right, and that the other thing I'm very much factoring in, and what I'm doing over here is the flux. I want to make sure that the flux, given this core material type and everything, I want to make sure that the continuous conduction mode effect is very much in force, that we're getting crazy amounts of power around the T2 cycle.
Yeah, exactly.
I think that's so I think that's an important thing that I never fully added into my sort of consideration set in the past. I always just expected it to magically be there.
Right.
All right. weird. I cut my knee today at some point, and I have no idea when I did that.
And you're bleeding everywhere?
Yeah, my knee's been bleeding apparently, and I didn't realize it until I just went to, like, you know, I sit down and I felt this weird, like, tension in my skin. I looked down, it's all this dried blood. I'm like, how the hell did I do that?
That's awesome. I know the feeling.
Weird. Sorry.
So I'm going to pick this value and I'm going to change this to about what? It's a high value. I always got to look at my common resistor values. I can never remember them all. See, 3.3, 3, and 2.2.
All right. Got through those series of experiments with only minor entries to my person.
2K. Is 2K a standard common?
Standard what?
I always forget the resistor standards. 2.2K is standard. 1.5.
Yeah.
So I'm going to have to do some more math. Let's see, I need to calculate that out. Let's see. 1K. I can do that. I can do two 1Ks and I'll have what I want.
You'll have 2K.
That's what I want. I was going to do it a different way, but I'll do it that way instead.
Yep.
Going to run them, and I was going to find the right values to make them run in parallel, but that would be stupid of me if I can put two 1Ks in series. Oh boy, sometimes I think about it in a difficult manner.
Hey, I think we all do that sometimes.
I need to punch in the real values for that too, I guess. Huh? Okay, air inductance. Let's see. 167. All right. Oh, let's see. Yes. I'll try what I did here. I was like, I hear an airplane outside. Oh, nope. Alex has an airplane outside. Because I'm used to helicopters and stuff. They're always out here. It's ridiculous.
That's
I was like, what is that? Oh, must be a
That's
helicopter.
Isn't that something?
I just measured 254.6. 254 at 252.7. Man, that meter just sure is darn accurate.
Yeah, I mean it really is. For some reason it gets very close to the calculated values.
Yeah, like I guess it's just because it's such a high frequency.
It knows how to find the best frequency for the measurement, and I don't. And our frequency, and the good meter quote is it's just a low frequency thing.
Yeah,
so it gives us. Yeah.
Yeah, it's just not designed for that particular frequency range, I guess.
And you know these characteristics are frequency dependent. So, but the fact that you can calculate them in a way that has nothing to do with frequency is sort of at odds with logic, you know?
Yeah, with how you measure it, I guess.
Like what exactly are you calculating in those measurements where frequency isn't frequency isn't factored in at all, except for, you know, pi. Twice around a circle is the only frequency aspect that's sort of in the calculation.
Mm-hmm.
I don't know.
Alright, today's the first test with pumping water through the system. That'll be fun.
Yeah, man, it will.
Because I think it might change at least my visuals. See if I can actually see bubbles at a certain given point in my testing versus shaking the cells at the end of the day and deciding, oh, I did something today.
Yeah, it's definitely nice to be able to look in and see the bubbles forming, or as you say, like see them circulating or something.
Oh, also sticking a fluorescent light of some kind into the water, detecting a true high voltage would be nice. It's just an idea to test.
We'll know when we have high voltages, though. We'll see that very obviously, and then at which point, yeah, those lights should fluoresce. Yep.
So I'm going to use this circuit. With this circuit. I'm not going to use a battery today. I want to try something else today. Because I need to build me a simple variable circuit so I can vary my voltage with a battery.
Oh,
I'm not going to do that today. I'm going to run out of time, but that's something I need to do. Okay. What's up? Lunchtime. I gotta go cook me my pizza. I need to go cook my pizza. You got extra? You do? I'll eat a little, but I'll let you guys eat first. Okay. If you say so. Let's see. But I do need another power source anyway. This coil. It's going to be there. Positive coming off here. Negative. No pulsing. Oh, I don't know if I can run this program. It's so slow. Excellent. Ow. Let's see, I'm gonna connect.
Did you see that tuned fall stat circuit I did? It was pretty nice.
Can you send me the code in a file when you get an opportunity, because that link, the Java never runs in my browsers, so I just have I have it offline.
Yes, you can. I mean, the link is actually in the post, though.
Yeah, I know. It's like the whole code's in the link, but it never works for me, so I can grab it that way.
If you grab it that way and put it in Firefox, you probably have a better result than if you try it in Chrome.
No, I don't use Chrome. I only use Firefox.
Okay, so then I don't know why. So this doesn't run when you try it?
It never loads right on that page, and/or I'm stupid. But either way.
Just copy the link straight into Firefox. Let me know if it doesn't work, because if it doesn't work for you, if it's not working for you, maybe it's not working for others. Though it does work for me from that page.
No, it's probably just me. I don't think I have Java installed in my browser. I have it installed on my computer.
That could be. Just might need the Java plugin on Firefox. In ways, it's been nice having my phone again.
You'll
It's
dread
totally
it.
disconnected. I mean, in some ways it's not, but most ways it is. Like just being able to get your mail and just communication is, I know, it's good not to be isolated.
Yeah, but it's good not to be overwhelmed by having that thing in your hand and constantly looking at it. That's the problem.
It's just discipline on that. You just, I think you're right. I've been thinking in my own head about that. Where's that line? And to me, it's just like, just don't look at it all the time. Just when you need it. If there's other stuff in there, when you need it, you can address it if you have time to address it at that moment.
Indeed. All right, we're pulsing. Now, I'm not going to connect this stuff directly today. Not right now, anyway.
All right. I understand. You afraid you're going to get high voltages?
No. No, not at all.
Right.
I'm looking for something else. I want to see if I can achieve my goal.
You're afraid that the scope might change the waveform if electrically connected.
Yeah, there you go. Thank you. That's exactly what I'm concerned about, actually. So, let's turn on some gating. Turn on some more pulses. Actually, I'm going to turn off gating. We're printing. Check something.
Okay.
I'm gonna eat some food. Yes? What? I know. Jose said I could eat some, so I will. Just got enough. Mmm. Ooh, coleslaw. And what is that? Rice? Rice is good. Yeah, I'll get some. You need to go get some.
What?
Did you get any extra forks? I'm gonna go get some. a nice day to be outside, working hard.
Yeah.
It ain't hot. It's almost cold. Probably gonna hear some static walking across the street.
I'll mute you. I don't hear it yet. There it is. Goodbye.
Oh. Chicken. What? She usually does, I don't know. I didn't see her over there.
You back?
Mm-hmm.
Okay. Wait, hold on one second. I'm gonna mute you.
I'm gonna try
Talk
to
to my
find
wife for a
some
sec.
resonance here. Mm-mm. So 1 is on my cell. Yellow is on my diode side of L1. I got more tuning to do, I think. Let's keep going up in frequency. You know, I forgot to add my resistor. Better do that. You know what? I'm not going to be able to use a carbon-based resistor. It's going to have to be a resistor. A real resistor. Did you hear me, Alex?
I do hear you. Yes, I'm about an ear on you. I'm just talking to my wife right now, but I'm listening. You're to use a resistor, a real resistor, not a carbon-based resistor. I think you said. No. You're probably saying not a carbon-based resistor, because a real resistor is not made out of carbon.
Yeah, and I wonder if if a carbon resistor won't work. It's like trying to add a carbon resistor on a dummy load of a repeater transmitter or something like that. It'll just blow it.
Yeah, it's not.
So if I want an impedance match, I'm gonna have to use a resistor, a resistive resistor.
A mica one or something like it. Yeah.
Like a wire round. Think about that one.
What's that waveform right there? You got some oscillations going on.
Hey, where's the weight from? Yep.
That waveform is the blue trace is the positive side of my cell. The yellow trace is the diode side of L1. And actually, I'm going to hook up. Oh, I already have it. Earth ground is connected to the floating ground along with the scope probe. at 1 volt input, by the way. And there we go. There was something. Small, but it's there. Look at that. Hey, look at that. You know what that is? And I can't hear you, by the way.
Sorry, I was sitting there talking to you. I was muted. I didn't realize.
It's okay.
Yeah, I like that. I see little oscillations on the blue on the diode side.
Well, the blue is the positive cell. Look at that. Positive potential.
Blue is the positive side, yeah. And the yellow is the what?
Diode side of L1. But what I like about this is I'm getting a positive potential.
On that side.
Yeah, and so I'm wondering if I'm getting any sort of... See what the scope signal shows me on the negative side.
It is nice. On the negative side, you're getting a negative side.
Trying to tune this in and I accidentally hit the wrong number. I don't think I'm really truly in resonance yet.
Can you easily scan your frequencies? See where the amplitudes are high?
Yeah, that's what I'm working on actually. I just happened to stop here because of this result.
Gotcha.
Look, if I scoot this over a little, down, up in frequency, I can get that like double oscillation there. Maybe that's not positive. Hold on, let me get this.
It might just be an amplitude modulation of a.
But look, it's flattening out.
Yeah.
It's definitely more positive than negative.
No question, but I just mean it could be if you put two sine waves together, you can get something that looks just like that at certain interference points.
Right.
But yeah, no, I mean it looks good. So the other thing I would say is if you move your core around, you can probably cause that to change its shape as well.
Now, right now, the yellow is the negative side. I moved a little bit of something. Let me, oh, there we go. What's up with that? It's because I'm touching stuff.
That was some amplitude there. Did you just switch something?
I just keep barely touching things. Hold on. It's just changing capacitance is what it is. Let me try to retune this. See that? I'm touching the diode right there.
Mm-hmm.
Let me try adjusting the frequency a little bit now. That's basically across the cell. I'm reading on one side and the other.
That's okay. That's good. It's all in phase. Looks like.
Yeah. Try something here. There we go. I had to tune it back in. Hold on.
Are those the same voltage, the same time scales on both waveforms?
This might be the first time I've ever seen the cell give me two totally different signals.
That's good.
And they're both on the same scale, 50 millivolts, but I'm not touching the wire. I'm still saying this is not in resonance, as far as resonance is concerned between the inductor and the capacitor. And I only say that because of fine-tune this a little bit more. See, if I go one way, I get this mess. And if I go the other way, then I can get to that nice positive peak potential.
Yeah.
And then if I keep going, I get that same mess in the opposite manner.
Right. Comes down the it's like you're lining up two waveforms and the additive nature of them is making them super tall, and then you can slide it You can slide you can slide that waveform to the left or to the right, which brings down the overall amplitude. Which, by the way, is kind of why resonance works.
Don't forget I'm at 1 volt, by the way.
Yeah, right.
So if I adjust the amplitude,
Start going up.
that's 6 volts.
When you were at 1 volt, though, did you get the 1 volt input? What was the amplitude of the blue? Was it more than 1 volt? We can't see your divisions.
Well, I'm not touching the wire. So I'm at 2.5 divisions at 50 millivolts DC.
Okay. And that's with 1 volt. That's 1 volt in.
I might connect it directly.
Yes. Let's see. That'll help us know what you got.
Look at that. It's all positive potential.
And what is the one? Is that 1 division
That's
at 1 volt?
10 volts peak to peak right there.
With 1 volt input?
Actually about 13 volts peak to peak with 1 volt input.
Okay, that sounds like resonance.
That's pretty good actually.
Yeah, it's good.
So let me connect the other probe to the actual wire and just see if it totally screws everything up. I'm gonna have to retune it to get this back. So here they are on the 0 line being 0 line, okay?
Mm-hmm.
So one's a higher potential and one is truly a lower potential. They're the same waveform in this manner though when I connect them electrically. Let me try to scan it a little bit here and see if I can adjust into anything special.
Okay.
Because that capacitance of the probes really does screw it up.
Sure, yeah.
But remember, I'm earth grounded. I'm grounded on the floating ground, so everything is truly reading a 0 point, not a floating 0 point, because that'll screw you up.
Yep.
And I only have a 1 volt input right now. And that blue probe is definitely above the positive line. Actually,
At 13 volts too.
it peaks slightly below, but give or take.
No, that sounds like. And what frequency are you running there?
16 right now, but let me just keep adjusting it because it's actually
16K or 16H?
16K. No. Yes.
I'm gonna say really low otherwise.
It's nice to see that they're offset because normally they're not.
And that's on either side of the cap.
Yeah. See here, I'm bringing the frequency down.
Yeah.
This is the first time I've ungrounded my scope, by the way. But in theory, I'm regrounding it exactly the same.
Mm-hmm.
That's 8K, 7, or just past 8. So you can see the double ripples and stuff now.
Yep.
But it is positive potential. I wonder how I can... I guess the magnetic flux is what's going to keep that negative potential negative. Because the positive potential is... Or actually, no. Maybe I'm wrong. Maybe it's the diode. I'm trying to figure out how we think the circuit is going to keep the negative plate negative. Because you're constantly pushing, positive voltage through it. It's going to just accumulate negative voltage on the other side, but it's not.
Mm-mm.
Every result I'm seeing right now, it always seems to be the same signal on either side, and that's great, but it's never like a full-blown on a high or low potential. You know what I mean? It's always something similar to what I'm seeing now.
Yeah, no, I'm with you. The fact is, I believe that
There's coming back into that point. 14.
after the electron bounce, you don't see no voltage negative voltage is applied to the cathode plate any longer, because and before it's certainly applied, but only long enough to form the positive voltages, and then so I just think after it changes mode, you just won't see any. The only charge that will arise on the cathode plate is the response that the capacitor has to the mounting charge on the positive plate.
Yeah.
You know what I'm saying?
Yeah. See, I think, in my opinion, this is, in theory, we just passed resonance, but...
Did it start going back down?
Well, all my peaks got tiny. I'm just going to let it go. It's at 26K right now.
Okay, yeah, just watch it for a while. See what it...
But I don't understand why there was such a broad range there where I saw a nice potential voltage.
Well, how many hertz was it across that you had the high voltage, that nice high voltage span?
Let's see, 14.
Because usually it's resonant at the resonant frequency plus or minus 5%.
Like here, it's starting to get a nice peak. We're at 15K.
Yeah.
We're staying about the same, staying about the same, staying about the same, staying about the same. Now it's starting to kind of fade off. It's at 18.9. It's a huge range.
Pretty big range, yeah.
Let me go back.
Yeah, because usually I would see it like, let's say resonance was at, say, 3 kilohertz. I would be, I would see increased amplitudes fading off, rolling off either side by like no more than 500 hertz. And the scale of that, the lower the frequency, the longer that scale, the longer that tail is. The higher the frequency, the shorter that tail is. And that's just a function of scale, frequency.
So right now, I'm going to put these on top of each other. Right now the yellow's on the diode side of L1. So let's scan again and see if I can find where it has anything special. See, in my opinion, that's... See, there's something right there. That's kind of special. See that?
Special.
Look at that. So this is where I was earlier. That's the diode. Look at that. That's interesting.
Is it still going on where you change the frequency and the little second notch goes either to the left or to the right based on frequency?
Wait, I'm sorry, what?
On the blue line, if you increase your frequency, does that second sort of peak roll through the higher peak? Does it roll across, through the other peak and to the left or right side of it, depending on frequency?
Let me keep going.
Yeah, it does.
So let me put these on the same scale for a minute. There, they're on the same scale. I'm putting 1 volt in, don't forget. I'm electrically connected. This should be accurate measurements. So there, we're rolling. See it rolling?
Yep.
But now I've got 2 peaks.
No, that's
Look at the phase. Look at the phase shifting. See it just rolling into that other peak. All right, so there you go. So yellow is the diode side of L1. Let me double check. Yeah, diode side of L1.
okay.
And let me just make sure I got those right. Yeah, L1. Diode side of L1. And I'm at 7K. So let me go up at 50K a pulse. So watch it as
And
it
what's
goes up.
the blue one is the anode of the cap?
The positive, yeah. So there we just lost a peak, gained a peak, lost a peak. Now we're sitting at an equal-ish peak. Now we're moving through it. We're at 12K, 13K. In theory, I tuned this at 7,500.
Can you go back to where you had that really nice peak and then take the inductor out of L1 and see if it goes away, if it's greatly reduced, so we can make sure that that's like the back energy from when L2 is turned off?
My coils are pretty well set in stone at this moment.
I see, okay.
But see this? In theory,
It'd be great if you pulled that core out, if we saw the second one go completely away. That'd be a nice confirmation.
oh, that second peak.
Yeah.
Look at that really nice sine wave on that yellow.
I love
gray.
that those three incremental peaks. That's awesome. I don't totally get them right now, but I would get them more if we could move the core.
Yeah, I can set that up. Just not at this moment.
Yep.
Let me set my trigger. So I'm all the way at 4 kilohertz, 3, 6. So now I'm getting multiple peaks into my yellow trace, which I don't really want. But you gotta remember, I'm at 1 volt here. So what I wanna try to do is start at 1 volt and get where I think I wanna be.
Mm-hmm.
And then once I think where I want to be, I'm going to slowly turn the voltage up and try to keep tuning into that peak and just see what happens. Yeah, see those like multiple peaks in there?
Yep.
I think I'm going to set it. Let's see, the blue trace is on the positive cell. So what I think I'm going to do is I'm going to get it to where I get 2 peaks. I'm going to call that frequency doubling for fun.
Okay.
And actually, let's measure it. Let's see if it truly is frequency doubling. There I'm at single peaks. Now I'm going past. Oh, now it's dying low, see? So let's go back to where I had 2 peaks and measure those 2 peaks and see if it is half of my frequency. Actually, I don't even know if the yellow trace is my frequency. Let's try that first. See.
That's true.
Let's just get that.
Because right, we might be so far in, it might just be an oscillation of the primary frequency. Yeah.
There.
We'll see.
That looks okay. Let's measure that. So the blue one, from one double peak to the other double peak, and I like frequency, it's at 9.6K and I'm putting 9.2K in. So
well,
actually the blue is actually, oh no, I'm in theory right here, I'm actually measuring yellow. So let's switch to yellow. And I should be measuring right at my that's 1.2K. Yellow is my input frequency. My output frequency is doubling. So now let's turn the voltage up. And
see if that nice effect holds.
And see if we can keep that. And at what point we need to rechange stuff here. I'm going to try to tune this a tiny bit and see if I can keep that really nice looking double peak. And actually I'm maxed out on my scale, I'm at 10. But let me just try something. Let me just try adjusting it and see if I can keep that double peak nice. Now I'm almost, that's kind of odd. I'm gonna have to retune this. Ooh, what's this noise I hear? That's definitely my cell ringing. Let me turn it back down. and put these on times 10 because it's a totally different probe effect. So times 10, times 10. See, it's all goofed up. Let me retune to where I'm happy with it, and then I'll try to bump it up some more. See all that mess just from the times 10 scale thing?
Yeah.
Actually, let me put it back at, what was it, 9.2. 9.2. Oh, okay, that's close. Look at that nice double peak. There we go. Look at that.
Yeah. Is that at higher voltage? Wow, that is good. Now wait a minute. That's double peak. The yellow one. Okay, so can you put a probe on your gate?
I'll have to move one of them.
Yeah, move your diode.
The diode's my pretty signal, but I'll move it. All right, so you want to put this on my gate. You want to...
I want to see how those are relating to pulse on, pulse off.
Okay. This one. Oh. Huh. Look at that funky looking thing. There's like, there's missing pulses.
Yeah, it's just it's just like harmonic. Can you zoom in a bit so we're just looking at one? I want to see what's happening between T1 and T2.
There you go. There's a still shot of it.
Now now that's a whole train, not just
Oh, you
a
want
single.
this one? Oh. Nothing.
Yeah, so we're not. It's not apples to apples here. We're getting large effects over the whole scale of the train versus what we need to be seeing, which is incremental increase on T1 and then another incremental increase on T2.
Wait a minute. What's really happening right here?
Are you on the same time scale for both probes?
Yeah, I can't adjust different separate ones. Look, this point to this point is 24 kilohertz. And I'm at 12.5. And then if I zoom in on one of these peaks, this is actually 5 megahertz.
5 megahertz
So what I'm telling you is these intermittent pulses are happening on their own. What you're seeing right there is the pulse frequency. That's one pulse.
That's T1 and T2.
That intermittent resonant thing going on right here with this yellow trace
Yeah.
is something totally that I am not putting into the system. It's all by itself.
So it could just be noise, but whatever it is, it's okay, good. So we're looking at T1 and T2 there, right?
Yes.
Now, can you scale back?
T1.
Is there gating on that? So we can just confirm that when we go all the way back out?
Yeah, let me turn on gating because you're right. I need to do that.
All right, good. Now go back in so I can look at T1 and T2. That's good.
Let me, so now you see what that's what I was
Yeah,
saying.
no. This is exactly what I wanted to make sure of. So good. So now we've got a pulse during T1, and we got a pulse during T2. but are they totally rhythmic? Can you go zoom back out for me? I want to see if it's rhythmic. Um, so okay, every time, yeah, it is. It's very repeated. So during T2, we've got our big pulse, and during T1, we see the thing increase over the course of T1. But when
So-
when T1 turns off, we get this big dip, followed by, yeah, that all adds up right there. That's a nice result.
And I'm
Screenshot,
at
screenshot
one.
that bad boy and put it on your Google profile.
Google. I'm at 1 volt, so let's keep trying to turn this thing up.
I'm gonna mute you for 1 second. I got a Jeep coming in. 1 second. Okay, I'm back. That was a really nice look, a really nice view you had there, and I think that pulse in T2 is legit, man.
Well, here's what I want to do. I'm starting small again. I'm back on the diode side. Now I have gating, so I can really see what's going on. And as you can see, when the pulse turns off, alright, so see when the pulse turns off, you have an opposite
High fire, Pinto.
opposite self-resonance going on. So
I don't see where the pulse turns off.
right here.
Okay, it's
See
hard
the
for me to
double,
see.
double, no double anymore. That's because it's off.
Oh yeah, right. Okay, so yeah. So now, okay, right. So during that, can you? Yeah, so I can see it better. That's a little better. Okay. Oh, you know what's the problem for me? I think is I want to see. I really want to see the gate, but you want to see the diode.
Well, I don't have that many probes, and I want to see what happens when I start turning up the amplitude, and the only way to see that across the diode is to watch it. So, for now,
It's okay. I mean, we know that the input frequency is both the same on both sides.
I need
Man.
to. Is that 2000? I'm going to turn off gating for just a moment so I can see what in the world I'm looking at.
It's all positive though. Look at that blue.
Yeah, it's all positive potential. That's right. You see the
Yeah.
the blue, how it's got this funny looking extra?
Yeah.
That's where the pulse on and off is happening. So
Yep.
so if you can see it, that's what
I see it.
that's what you're seeing. So now you know where gating's at, by the way. Now you know where the pulse on and off time is, by the way, I should say.
Yeah, that's right. That can be our gate.
So let me turn the voltage up. I'm gonna go 1 volt up. Now I'm at 2 volts. Now I'm starting to see. All right, so let's tune a little. Let's see if we can get those. Well, they never really were perfect because the off pulse is higher than the input pulse because of the flyback.
Right.
So actually that's okay.
Yeah, you're good.
But look at this, I'm adjusting amplitude.
Garage, because it's going to start falling apart. The garage door. insert the cave in more.
Yeah.
You gotta glue it or something.
Well, that looks good.
See,
Which core is this that you're using? The one from the other day? I mean, not core, coil?
yeah, the new set I have. Wow.
This is a nice result.
So, like, I'm going past, right?
Yep.
And then I'm coming back,
Julian?
you know, and I can get to that point where I can get that right here. And actually, I need to take my tuning down. Right here, I can get to where, look at that, all positive potential.
Mm-hmm.
Let me turn this so I can tune it a little bit. I'm at 50 scale, I'm gonna do 5. By the way, I'm using a power supply as my source, and I'm still getting decent results. Let's see. Let's put this on, that's the same time scale, look at that. That's the same scale.
Yep.
I'm only getting about 20 volts, but that's a magnitude of 2. I'm putting 2 volts in, so alright, I'll take that.
Yeah. It's nice.
So I guess I don't know what to tune for in this point. Should I tune for maximum voltage?
Well, it depends
I
on
like
if
this.
we're interested. If you want voltage, that's because we want to see water, stuff happening in the water. But I don't know if that's what we want right now. I think what we want.
But you see how I can get this flat?
Mm-hmm.
Do I want to see a double pulse? Do I want to see a flat? Right
I think
now,
we want. We want to see activity in T2. That's what we want to see.
and this is what I'm thinking. So even though my diode shows less voltage, I do want that extra peak in there. So let's tune.
Yeah, because all that diode is showing you is on the L1 side of the diode. All that's showing you is what's happening when it gets blocked. I mean, we don't even care about that really. It's enough just to look at. It's enough just to look at the anode of the cell, frankly.
So let's go up a little bit more. See, I'm getting off. Oh, I went way too far. There's 3 volts. So
Can you give me the gate again?
yeah, that's what I'm gonna do.
I get a lot more information from that gate than I do from the diode.
Right here and right there.
I see it, but
Yeah, I can hook it up. The only problem is it affects my entire circuit and I have to retune it.
okay. If this is what. Okay, then let's just leave it here. So let me just see. Right there, it starts, and there it stops. So okay, there it's. So L
Look at those
stops.
intermediate. Some of these have. Look, there's a pulse every once in a while that don't have these.
Yeah,
I don't
it's
get
not being
that.
painted the same way.
I'm not gonna worry about it, but isn't that weird?
I think it must be. I think it's a tool glitch.
It's got to be my input pulse frequency going on, but it's okay. So here's what you're seeing.
Yeah, this is good. So during a time it's on.
It's got a
We're actually-
little peak.
Can you zero them both?
Zeroed.
Yeah, I see. That's cool stuff. How were you here, Fire Pinto, when we were doing that crazy like discharge weirdness off the water?
No.
That was cool stuff. And then what we're doing right now is pretty good.
He was here this morning.
Let's see. Yeah, go back in. Be good. So that's T1. That's a single T1. And while it's happening, we see the charge coming up on the cathode. And then when we turn it off, we see this huge charge, not the cathode, the anode. We see this huge charge coming back from L1 on the anode. We see a few of them.
Let me try tuning with it set up just like this
Okay.
to see if we can get those to match a little better. So like to get that,
frequency-wise.
yeah, to get that off time to really.
The thing is one thing should be responsive to the other. You know, we should be able to like dial it in that way. But let's try it.
No, I mean, Like
You know what I mean?
No, I guess not.
One thing should be like these result. It should be like we should be able to tune them independently of each other because the effect is tied to the cause of the thing turning off.
But see how. Let's see. I turn it on. I get a low, and then a peak, and then halfway down, I turn it off. And it slams into this nice high peak, and then I turn it back on at the right time, and I get this nice little oscillation. It's almost like I'm.
It's like charging
like,
when it's on. Then you turn it off, and you get this big peak coming probably from the other direction. Although it doesn't look like there, it's coming from the other direction. There it looks like a big. There it looks like two. Like it's. It doesn't look like it's a response there. It looks like it's like a. Even well, it looks good in ways, but yeah, I just don't like the fact that it's like doesn't seem causally tied to the drop of T2 or T1.
But look, see, I'm tuning it in to where it is now, and I'm getting higher amplitude on the flyback. And
yeah, that's true.
See what I'm saying?
But look at that.
So if I can get it to turn off, yeah, see, that's what I'm saying. If I can get it to turn off and on at the right time, then yeah, then it is a cause and effect. I'm just not tuned. You know what I'm saying? That's
yeah, but the one thing that's missing from that picture is
yeah.
Why would the effect, the thing you should only see if the effect is working, in the way that we suppose, why would we be able to dial it in this way as if it were independent?
See there, I'm starting to get another peak on that far side.
Yeah.
It's because I went too darn far. I wonder if I need to go the other way instead. Let me just sweep this the other way and see if we can get us something that we're looking for. I need to think about your question here. Let me get done messing around, and then I'm going to think more deeply about what you're asking me. So
No, it's okay. I mean, I'm just raising. Something comes to my mind when I think about how we're seeing the behavior on the anode given the energization on the MOSFET. It doesn't totally add up in my head, but it's okay. It's still, we're seeing really good stuff here, and it's worth exploring.
See, here's I don't have a double peak, but I'm getting a nice, that's what you would expect to see, in my opinion, right there. On, going down, off, swing up. On, going down, off, swing up, and like keep that oscillation going.
Yeah.
But now I'm at an AC oscillation. I'm no longer where I want to be. I'm no longer in a positive potential. Now I'm in an AC swing, and that's not what I want.
Yeah. That's pretty. But you can dial it with.
And even though I'm in resonance, look at that. I mean, I'm in resonance, right?
Yeah, clearly.
I'm more towards resonance than I was earlier, clearly. But maybe that's not what we truly want, is a pure resonance system. We want to see that doubling effect so that we can get our positive potential.
Yeah.
And so I'm going to go back. I'm going to tune this thing back to where it looked kind of good. Again, I'm at 3 volts input right now.
3 volts input, and what's coming out? 13?
10, it's 50, 150 right there. Swing.
Oh, we're way up. Okay, yeah.
That's
Before we were at 1.
And that's
before we were at 115.
That's on the cell.
Yeah, good.
Now, for fun, let's see what my meter's showing. My other meter. I'm showing 0.04. My voltage is slowly going down, as if tuning this thing in is neutralizing the water in the cell that I'm not using. I'm using it as a test bath.
Mm-hmm.
It's kind of interesting. See here, I'm going back down, but I'll get right here, and I'm going to get somewhere in here. I'll get back to that peak.
Mm-hmm.
There, I'm looking for right now. I'm starting to get 3 peaks again. I'm just trying to find out where I was better off seeing more of a positive potential than a negative potential, or than an AC swing, I should say. I think that's for some reason I feel that's important, Because that's what we're looking for, not necessarily a doubling, but surely a positive potential at all time.
Positive potential at all times, and that what do you call it? The continuous conduction mode, which is we seem to be able to trade some resonant voltage for it by adjusting frequency to be just so.
There, I'm
Which-
almost fully positive in the potential. Although it's not very pretty, it is positive potential,
Yeah.
right? So let's go a tiny bit more. Now I'm starting to get past, I think.
And it's funny because now it's like we're charging up just a little bit while we're on. We are charging up, but just a little bit while we're on, and then it turns off and it goes crazy. But that doesn't seem to be back EMF though, because it's connected. It's connected to the on swing.
But maybe it's not back EMF that's doing the work. Not as much as we think it is.
Well, this scope trace suggests that.
See, that to me is great. That looks awesome.
It does look awesome.
I'm gonna go up another volt.
It's just weird about what's happening in T1, isn't it?
And I'm using like 0 current, by the way. Let me put on a I have a nano amp scale now, so let me slap that puppy on there. I'm just curious to see if that's what I'm reading in the nano scale here, because I'm not reading much on that scale. Micro amps. So we can pop this one. That'll be easy to do. I'm over 100. Let's put on my other scale, milliamp. I was on a milliamp one, but I was using my one that burned up, so it's just for measurements. Man, I'm not showing anything. Like, all right, I'm gonna leave it on this scale, and I'm currently reading. Let's see, that's 100 milliamps.
Okay,
So
that's great.
So that's 10. So that's 10. Let me verify. The only way back to the power source is through ground, okay? Right?
Okay.
The only thing else I can say is possibly I'm using battery power somehow through that circuit. That's okay. I'm going to pretend that I am not. In theory, I'm using nothing.
Well, the source of your power is
4,
what?
3, 2. I'm at 2 milliamps, which is why
That's
my 100 microamp meter, I guess, was pegging. All right, I'll take that.
And then your voltage is at around 200 volts with a 3-volt input.
10, 20, 30, 40, 50-ish.
50 volts with a how many volt input? 1,
5.
2.
What? 4 right now.
Okay, 150.
Let me go up a little more. See, now I'm dropping below the negative scale.
Yeah, we want to. Yeah, we want to keep things positive.
I'm gonna try to tune to where I'm not.
I like this unipolar thing.
See, now I got a dip on the on time. It's not what I want, in my opinion.
Hey, Fire Pinto. Yeah, we're looking at this. Each on is T1, and it's not stepping in the way that we usually think of it, which is kind of what I was calling out earlier. But we are seeing some very interesting energization in keeping with other ideas that we've been working with, particularly in terms of the continuous conduction mode or the inductive frequency doubling. And that's kind of what we're exploring here. There is a disconnect, certainly, between the way we've always thought about things and what we're seeing here. But this is very interesting enough to think about and think through, and so that's why we're on it.
I can't seem to tune back to where I'm getting that other peak where I want it. Let me just keep swinging through here, but I don't think this is
Great.
right.
Great hanging out with you too, J. Rodney. Those aren't actually pulse trains. Those are the pulses within the pulse train. Each one of those yellow blocks is T1, and each one of the off times, that's T2. You're looking at we're microscopically focused in on a single pulse train there, and then what we're looking at is the energy swing on the capacitor during T1 and T2. That's exactly what you're looking at. And what we're seeing is as we adjust the frequencies within the range, we're in the range of resonance. As we move the frequency around to the left or right, at that point, we're able to better make the capacity. We're able to control the extent to which this doubling effect occurs, and it seems that it needs to be tuned frequency-wise, at least from what we're seeing right now. And then after we turn it off, as you can see when the gate's off, the T3 time, there continues to be an oscillation that resulting from the last time that T2 turned off, as you can see right there.
My goal at the exact moment is to keep a positive potential.
Right, we want a positive potential and we want to maximize the continuous conduction mode, or i.e. pulse doubling.
Yeah, that's kind of what I'm trying to see here. There. See, that's a problem. I'm having a problem with my own scope. This is, stop this so I can see it. You see where there's, you see this?
Yeah.
And that, and that, and that, and that, and that. That tells me that I'm not quite right. I should see that nice dip on every one of these, but I can't seem to achieve that. I want gating on for purpose. I want it on to be on. Let me put a couple more pulse trains in here. Let's do like, let's just do like 20. That way I got some serious time to look at the actual pulse train.
I'm surprised by the amount of oscillations in T3.
Yeah, and look, it takes a bit. It takes some time to get.
Yeah, it does.
Let's measure.
It's like it oscillates like crazy, and then it just starts swinging for quite a while at an undampened. That's weird, actually. I guess it's because we have so much inductance in that core, in that coil.
This is 13.8.
Okay.
I'm sitting at 13.8.
That's a resonant frequency of 13.8 K.
I'm sitting at 13.8 input frequency.
Oh, input frequency.
That's also input frequency. I'm telling you, it's both.
Okay, good. That's what it should be. Got it.
This freelance oscillation over here that's going on.
Yeah.
The one I'm measuring currently.
If your ring and your input is the same, that's what you want. So that's what you got. And that's
look.
This
right. Ring is all positive potential.
Yeah.
But yeah, if I measure, that's 13. That's 13.8. If I measure, let's just measure.
From first T1 to between two first T1s.
That's also 13.8.
Yeah, so that means you're pulsing at the resonant frequency, which is what you want.
Or close to it. Let's see. Let's zoom in a little bit. I still want to see that peak. I want to see more of that. Hold on, I'm gonna have to connect my. There you go. I disconnected the earth ground. Look at it.
I can see. Yeah. You got the 60 hertz in there.
Yeah. Let me hook this up to my trigger so that I can trigger on the proper timing here.
Mm-hmm.
Hook up my earth ground to my scope. Look at the positive potential there.
I know.
Look how high up that amplitude of that positive potential. That's good stuff.
It is.
So let's see. Now I can set my trigger back onto this.
Put your voltage up to 12 now and see what happens in your in your cell.
Well, here's the thing. I want to do it a tiny bit at a time because I've already tried that in other days, and so I'm just trying this at a different methodology today.
Well, I'm just saying, don't change anything except your input voltage.
Oh, it sucks. Watch. I'm at 5.6 volts. See the negative?
Yeah.
I want that to go away. I don't want that. I'm at 12 volts.
The swing and the underneath, you mean?
Yeah, I don't want that at all. I want that to go away. It's just my goal right now.
Okay.
That's
Well,
why
you're always going to get some. I mean, the
see,
higher.
Look, if I go back
Do it.
down to 3 volts, I can keep it fully positive potential.
Yeah.
So I feel that if I keep trying to tune until I get it right, I can keep that positive potential. That's what I want to see right now.
All right, let's just go volt at a time.
So I'm back down. You can see what it looks like. It looks nice. It's all above.
Yep.
And I got that nice double oscillation. So,
Well, really, it's like a single oscillation. Our first oscillation is so small. It's like it's within scale of the input signal, which is weird. But it's okay. Let's just see where this leads.
I mean, that's 1 volt right there.
Yeah, that's where we see like a true double.
Yeah.
But as it increases, that secondary energy oscillation gets so big.
Yeah, exactly. So, just for fun.
And it's also not really step charging that we're seeing, but it's
No,
good stuff that we're seeing.
It's not step charging, but that's okay at this point in time.
It is. Let's just explore and see where it leads.
So let's do a quicker frequency sweep. Let's see if I can find anywhere where that's close to holding. It's so slow. There, see that nice double peak? Let's keep
It's
going.
like, yeah.
Oh, now I'm getting some weird. Let me zoom out a little so I can see. I'm getting some weird oscillation going on.
The weird thing is how the peak during T1, the oscillation peaks before the end of T1. It's like, oh yeah, he's gonna turn off soon. That's kind of
exactly.
strange.
It's like you know what it is? I know what it is. The back EMF is trying to go negative when it turns on, and it says, nope, go forward. And then when it turns off, it's like, it's before it turns off, but I think that's part of that secondary oscillation that's happening when the flux is fighting itself, if you will.
That could be.
Okay, so I've got 5 volt in. Definitely, I wouldn't consider that step charging, but
That's okay. It doesn't matter. This is just pure research here.
so let's go 6 volts. And I'm pumping water, and if the bubbles are that small, I actually can't hardly even see the darn things, but I don't think I'm seeing anything. And that other cell it keeps dropping. It sat at 0.8 for the 3 days I've had it on my bench, and now it's just dropping. It's at 0.034. It's almost like it's neutralizing. So let's big steps here, but let's see what happens. It's like slowly walking off my screen. Oh, that's because of my frequency changing. So that's more positive potential than I normally get.
Yeah.
You know what? I see it. I can see it starting to do what I think it's doing.
Yeah.
Yeah, but
Oh, let's just keep
good.
watching.
Can. What are we?
just gonna let it go for a while. See, I don't like those negative oscillations. But, you know what? The double oscillation that goes negative is actually the on time.
Right.
That's kind of odd. Because look at that, like...
There it's like the on time, it's swinging super negative.
Yeah.
And then and again, it's like during the peak during the on time. That's what makes me feel like it's not causally connected, because unless it's as you suggested, the flux is like fighting it in the back. There's but none of that's sort of like ringing true in my head at the moment. But it's not. It doesn't mean it's not happening. But it's cool that during T1 you got it energizes, but then halfway through T1 it hits a peak of its own accord and starts dropping down. And then when it turns off, you get this crazy swing on the way up, but it like anticipates it, which is strange.
Yeah. It's
Also,
like it knows
also
it's
the fact
gonna
that it's
happen.
frequency dependent is weird too. Well, it's not really weird, but
See, that's a... Look at that double swing going on. It's like it turns off, starts to swing down almost before it turns off,
right.
and then it's off. And then it swings up, like that's the back EMF if you want to look at it that way. Then it swings down. Oh, you know what that is? That's the oscillation. Let me measure it. I bet that's the proper frequency, that 13 something.
The oscillation during the, I mean, it's like,
See,
it's
this
like
point to this point, that's 34K. That's 20, that's 15. That 13.8 I was at earlier doesn't really match up with my thought at the moment. Just to see if I could find it in here somewhere, but alright, well I'm gonna go the other way because I'm not liking that negative swing in the on time. So let's go. I'm at 8K. I went down pretty far. Now everything's moving up. Boom, right about in there. See, that looks good to me. Even though there's some negative oscillation, it still looks good. Now we're heading more towards... I'll let it swing back over. Now that's just like a true oscillation. See it? There's not much going on. We can get our amplitudes up, but that's not what I want. I don't want... See, I can get this thing way up. Look at it. That's not what I want, though.
mm-hmm.
That's an AC wave. I don't want an AC nice wave. I want that positive potential.
Well, but look, see that? I mean, look at the charger. That's step charging.
I know, but it's not step charging.
It is, though.
No,
I mean,
no, it's not. And I
the
say
amplitudes are swinging on both sides, granted, but it is step charging.
Right, there's
Look
your
at-
on, going up, slams on, goes down, slams off, goes up. But the problem is that's not what I'm looking for. I'm looking.
Well, but don't operate against the preconceived ideas. I mean, that's what we have now. To your point, you want to get that whole bit under zero gone.
But I'm
and
not.
I'm with you.
But I'm not frequency doubling either. See. In theory, we should see a frequency double if we're going to see the right thing. And then when we do see frequency doubling, we can see a positive potential. I mean, it makes sense. I understand where you're at. I'm just making sure you know where what I'm truly trying to see.
No. I believe me. We share that goal. But if you go back to where you just were, we had that really nice thing going on. Okay, what's that?
22K.
22K. We got it looking good above and below, but we don't want the below. And when you zoom in on it, what happens is, can you go in one more time on it for me? Okay, so And are we sure that's in like it's all in time phase? Like there's no weird like it's all in the same time?
Uh-huh.
Okay,
And
so
then
let me
look,
look at that.
look down here, the oscillation just completely disappears.
Yeah, which is what we would normally expect. But let me see that again. Zoom in for me. I want to analyze that if I could. Okay, so time on. It's weird. It doesn't look right.
Well, it's swinging. It's saying, okay, I'm going up. Turn on. Swing all the way down. Turn
Yeah.
on. Swing all the way up. So, I mean, it makes sense. It's almost like it's inverted, but that's okay.
It's just so disconnected from the.
Well, the only thing I can say is maybe it's it's not inverted, but it looks inverted. Like if the blue trace was flipped, then it would make sense.
That's right. It's like they're out of. It's like they're not in true. It's like they're out of phase. Like they're not. The instrument isn't showing, putting the yellow one on top of the blue one, right?
I don't think I can even do that. See if I can.
I mean, if it's all in real time and this is what it's saying, we have to take its word for it. But
Yeah, it's all in time.
so okay, so on. While it's on, it starts swinging down, and
Makes-
then while it's off, it starts swinging up.
Yeah, I mean it's almost peak to peak. See, and when it is peak to peak like that, that's when I get the best potential.
Yeah, it is.
It always is. It always has been when I get that swinging like that. But but I disagree with. So remember I told you like every time I play with this, it's like I get these beautiful step chargings, and then at the end of the day I'm like shaking my tubes and I see gas.
Yeah.
If I let it sit like this, I will not produce gas. But if I change it back the way I had it and let it sit for a very long time, I think that's when I'm making gas. But I'm tuning out of it because I think that this is the right signal, but I don't think it's the right signal. I think it's the wrong signal.
I think it's partially the right signal. I think that we got
it's the right signal for resonance.
Yeah, I think that, I mean, I think it's the right signal for a lot of things. It's like in terms of the energization building on the capacitor, all kinds of stuff. But what's wrong is we're getting the net neutral, we need to get rid of that, the negative side of it, which we can do through adjusting the cores in the chokes, which we can do by, as we've been just doing, playing with frequency a bit, and also this continuous conductance mode stuff may play a factor. Anyway, we're on the right track here, but that view is where you have the nice step charging. That's that's a good view. And but yeah, like you said, I mean, when I put that view in on my side as well, I don't see any gas being produced either. So it's how do we get that everything below zero gone? And that's exactly what you're saying. So in short, I agree.
Yeah. Let's see. I'm gonna try doing something here. Yeah, it's just, and at low voltages, man, it's perfect. It's exactly what we're looking for. As soon as you start raising the voltage, it's not. Where's my time at? Maybe that's why it's so darn screwed up. Now it won't change on me. Oh, that's what it is. It's the first pulse that's all screwed up. The rest of them are good. Okay. So although this looks kind of dumb, I feel it's closer than normal. Now we can see it sweep the frequency better. I had the darn timing way out. But look at that.
Yeah.
It's now I'm going, I think, maybe too far, but I'm going up in frequency. I'm getting closer to resonance in theory.
It's like,
So watch it. It'll come into resonance and it'll just do its thing. See how those peaks are those little chumpy peaks? Those are, in my mind, I can see that as I'm getting closer and closer. They're about to line up, and then when those two peaks, you know, when the top and the bottom swing light up with the input and output of a gate, that's whenever you're always going to see your maximum potential. Now, yeah, that's why I see it. But let me try something. Let's go back to this. Oh man. See, look at that. Giant negative swing. I'm in the lower frequencies now. And in theory, this should be calculated resonant frequencies is in this range right here. And a matter of fact, it doesn't look that bad.
no, it doesn't.
It's not. It's definitely not like a step charging, but it doesn't look bad.
Yeah, I mean, for now we don't need step charging. Right now we're more focused on continuous conduction mode. And that's what we're seeing here, so I like it. When we bring the two together, that's when we're in business, I bet. Step charging and continuous conduction mode, bring those two things together.
So here's what I can do. I can set this to where you wanted me to move the core, and I'll do it.
Yeah, I think if we move the core, we can change that bit under, that negative bit, we can move it up.
Wait, you want me to find that resonance point, or you want me to do something different?
Well, you can just leave it right here and just change the core if it's not too hard to do, and then we can go to that other point if you want, and we can, you know, we can play with both parameters independently.
Well, let me go back to where I'm seeing a nice double pulse.
Okay.
That's gonna change. I mean, this is gonna change everything. That's okay. So like right there, if you look close, you can actually see that makes good sense. The peak, it's like the back EMF is going down and it says nope, turn on. Slam, it turns on, but it's still like oscillating. And that's why it dips back down, because that's the second oscillation of the two fighting each other somehow. So if I adjust then, and I will, the gap, the core of the secondary L1 side, okay, I'm moving them further away. Moving them further away, moving them further away. Now they're like really far away. Now they're like really, really, really far away. And I'm tripling my frequency now. And I'm just going to take it all the way out. Now it's off. I only got half a core in there. I'm going to take a blank core so I can push it in and out.
Yep.
There, they're as tight together as they can get. Right there.
Okay, so that's the core with the core manipulation?
Yeah. So, if I do the same thing to the other one,
Let's bring the amplitude of the upswing down.
let's take it all the way out. Put another one, blank one in there. They were almost touching, really. I did notice like this one, whenever I get this one pretty far out, like almost all the way out. Like let me do that. Let me just set this on top to where it's like almost all the way out actually. Oops, let me put this back in. There, like right in there. Now, if I tune this into true resonance, it'll be a really high frequency, but that's again, I don't want that AC wave, in my opinion.
But you do want the amplitude that comes at that point. So it's question.
I know it.
Yeah.
Don't punch me too hard.
Hey, no, I'm not. This is no need to be defensive, my friend. Just sharing the idea with you that I think it's very important to have that crazy amplitude. And I've wrestled with this for a long time. It's like, how do we manage that? How do we maintain that amplitude, but shave off that whole negative part? And that's exactly what we're talking about here. So it's okay.
Yes.
And by the way, shaving off the whole negative part is probably by taking the energy in this continuous conduction mode thing is the answer. Because that's repurposing the energy in a directed way instead of just letting it be reactive.
Yeah, exactly. So here we're gonna start climbing. Then we'll climb until we get to that point where it's a nice, beautiful looking wave. It's still out of whack. The first peaks are starting to be in phase. Remember, when they line up, that's when we're gonna see it. That's how it always works.
Mm-hmm.
And there it's growing and growing and growing. Oh, it's going back down now. That might have been it, actually.
Yeah, it was it. It was nice.
But that's terrible.
No, it's not terrible.
I'm gonna bring this.
It's very shapely. We just got to cut the bottom half off through continuous conduction mode.
Let's try something. Let's try. I'm gonna try some magnets. I know this sounds silly, but Nate was playing with them, and actually it was quite interesting. I'll bring it back up, though. Let's bring it back to about...
With the idea that he could, like, use the magnetic field polarity to pull the molecule, to reinforce the molecules?
Well, to actually get the potential to swing a particular way. Instead of relying on the magnetic flux the coil produces, you'd rely on the external magnetic field that you're inducing, which is actually a good idea.
Yeah, I played with a bit of that myself a while ago.
So, just for total
I didn't see any good results from it.
let's see what we got. I'm going to take 2 really big neodymium magnets. Oh, and smash my fingers while I'm at it. Ow.
Keep them away from your laptop.
Oh my. Alright, don't kill my magnets. I don't want to die today. I like my fingers. So, here goes some fun. This will be interesting. Ow!
Gotcha.
Broke it. Dang it! I have
tough.
not yet broke one of these. I am so glad my fingers aren't in there.
Yeah,
Okay, well, we know they work.
That's one thing magnets do, is work.
Look at that. Let me get some more scale here.
Yeah, and I gotta go pretty soon, and I don't want to.
Kind of forcing it the wrong way, but here, let me try this though. Still the wrong way. Do some tuning. Let's go down. Big steps down. Nope, I want to go up. I don't like that yet. Look, see that? There's that double deal again. Kind of the higher peaks.
Yeah.
Going
Oh, there we go. That's nice. That's getting better. That's much better.
Again, back where we were. Not really step charging. But
No,
see,
step charging a little bit.
could be step charging if I turn the thing down.
It's step charging. I mean, it's not super pronounced, but it's doing it.
It will. Here, it'll get back up there where we were. It'll take off. Let's see.
Yeah, it's heading there now.
Wow.
There's full-on resonance. Now we got to get rid of that bottom cycle.
I don't know. I'm gonna leave it here for a minute. And I'm just going to, just totally for fun, put a diode in between the cap and the. I
That's
just
cool.
want to
Let's
see
see if we
what will
can cut it off
happen
that way.
if it completely dies, or, you know.
No, it's good. It'll, let's see. It might even cut the negative part off.
That's what I want.
Although all that resistance will probably just, all the resistance in the diode will probably just dampen the whole thing.
Yeah, I mean, I'm not. Well, maybe it's because I'm holding it, but let's see. I just want positive to go that way. Alright, well there you go. I placed the diode in there. And it is trying to resonate very, very hardly. It is attempting to resonate. Look at that back peak though. When it turns off, it's all happy.
Nice. That's a nice looking step charge. I mean, it's got a lot of negative to it, but swinging and just no avoiding the swing.
Look at that. It's just like it's going right through that diode.
Yeah,
But look how much bigger the amplitudes are.
it's true.
Well, no, maybe not. They're about the same as they were.
Oh yeah, okay, you changed the time scale.
I don't know, I lied. They're much bigger. Much
What's-
bigger.
What's the amplitude scale right now?
100.
Wow.
10, 20, 30, 40, 50, 60, 600.
If we could take that whole swing and apply it to the...
But get
apply it
this,
to
the diode's
positive.
in the darn circuit, man. It's in between the positive and the choke.
That's weird. And cool. What's going on there?
Look, I'm going to take the... What?
That's beautiful.
Look at that. I took half the core out. I'm holding it in my hand. And it didn't change at all. Now that I've never seen.
Yeah, that's weird. It's just tell me where you have the diode once more, so I'm sure I'm clear with you.
The diode is basically in between the cell and L2.
Oh, on
L1,
that side.
L1, sorry.
Oh, L1. Okay, got it. That's what I thought. And
Look at
you've
that.
got the cathode facing which direction? The cathode of the diode. I mean.
So the positive side of the diode is going to the positive side of the cell. So only negative charge can flow through it the way I've got it connected actually. So in theory I've got it backwards.
Okay, let's do it the other way.
Let me flip it. Because actually, I just took it off. Look at that. It's not even It's not even connected at all.
Oh, okay. So that's just what we had.
I've disconnected the positive side of the cell. That's only the stuff coming from the negative. Choke. You know what I mean?
I do.
That's kind of interesting. So hooking the diode up the proper way, because I'm awesome and I did it backwards. And there it is. So let's retune maybe. Let's try going down. Oh. Look, it cut it. Oh no, it didn't. It's just doing the same thing as we did before with the double pulsing.
Yeah. But actually,
I need to go the other way. But I'm not getting high amplitudes though, see?
right.
A little bit.
That's because of the resistance in the diode, though. There's huge resistance in that thing.
Going up, going up, going up.
That's what I thought was going to happen.
And just, no. Maybe we were trying
That
again.
was it a second ago, I think, yeah.
Nope, it's still going. There it is.
Okay.
It's like it blew right. Look at that. It's like it blew right through the diode.
Yeah. Well, the diode only stops the DC stuff, not the AC stuff. Well, it stops it, but it rectifies and stuff like that.
So now what happens if I disconnect, or here? Now the inductance changes it. You know what that means then? That means everything we were seeing just a second ago was purely from the negative side, from the L2 side.
Mm-hmm.
Because when I had this completely disconnected, you could do whatever you wanted, nothing changed.
Yeah, right.
So look, so right now, the only thing connecting the circuit together in theory would be the probes, if somehow they were doing that.
Yeah, but that probably not. But yeah, you're right.
Through capacitance. So here, let's get that nice wave back, which is like right, still climbing, right there. So that wave right there is only happening because of the negative side of the circuit. So now if I change the inductance, yeah, see? So look,
Yep.
so check this out. So this doesn't even make sense at this point. Let me make this smaller so you can see what I'm doing on my bench. Secondary L1 right here.
Yep.
This is the primary. Look,
Yep.
take the core totally out.
Core totally out of L1.
Yeah, and the secondary. It's like those two aren't even in the circuit right now. They're disconnected, so in theory they're not.
So what are we getting? Okay,
So all that. So what I'm telling you is all that potential that you see on the screen is coming from the negative side to the positive side, where I'm measuring it on the positive probe.
Got it.
But look how high those amplitudes are. Only on the negative side. 700 volts.
That means that you're towards the negatives, but you're measuring that on the anode of the cap.
Correct.
So you're measuring it from the other side across the water, even though even though the energy is coming from L2.
That's right. So actually, that's a good thing in theory.
Well, hold on. It's strange. That
doesn't even make sense. The thing's not.
L1 is not connected at all.
What?
L1 is simply not connected.
Yeah, right.
Okay, so let's think. So what is it connected to? Nothing. It's just open-ended over there.
Yeah, let me disconnect. Let me try something. Let me unsolder. I don't trust jumpers all the time. Let me unsolder this. So check this out. You see that?
Yes.
I have the whole other side of this circuit completely disconnected.
All right,
That's
good.
only the secondary, I'm sorry, the L2 and the primary.
L2, primary and L2. Okay, so we got charge going through the primary, inducing a charge in L2. And that induced charge to L2 hits the cell, the cathode to the cell, goes across the water, and then gets measured by the probe on the anode. Right?
Correct.
Okay. And then nothing else happens because there's no other. It's just floating, just like that, right?
Yep, and it's not going through the probes because I've just disconnected them.
Okay.
I've just disconnected the probe that I would be going through if it was doing
So the whole other side of the circuit is not even involved here. Like, what's on the other? What's on the back half of L2? Oh, yeah, L2. Where's that? Is that just going to the diode?
Earth ground.
So the back half of L2 is going to the earth, and that's it. Done.
There, now it's disconnected from the earth.
So now the back side of L2 is going where? To the earth, and that's it. No, not even that. It's going where?
Well, it has to be going to the scope at this point because if I unplug the scope lead, it disappears. So it's got to be just going back to the scope, which may be neutrally grounded to earth. So it's possible it's still grounded to earth.
So let's think of that. What we have here. We're definitely not seeing oscillations between the capacitor and and L2. And can you connect L1 to the positive side and see what you get on the other side of L1?
I'm removing the diode. So L1 connected to the positive side of the cell, going to nothing after that.
Going to nothing. And see what's on the other side of nothing.
Oh, you want to measure on the other side of that?
Yeah.
Look at that.
Is that the far side of L1?
No, not yet.
Okay.
There's the far side of L1. Check it out. You know what that means right there?
That's awesome.
That means, what that means is that's the induced voltage going into L1 through the capacitor.
Exactly.
So, what can I measure on L2 by itself without hooking it to anything?
Well, we kind of just did that. You can't take it out from the cap or it won't resonate. It won't oscillate.
No,
cap has to be
no,
there.
I'm sorry. My fault. Secondary.
Okay, so on the secondary, you can just simply look at the positive side of it to see what it's doing every time it gets turned off.
Okay, so there. The yellow trace is.
So that's just okay. So it's a weak induction.
Yep. It's like basically it's like half. Actually, where am I at? The yellow. If I take this off.
You took the core out of it though, didn't you?
No, it's still in there.
Okay.
So if I measure. Okay, the blue trace is the other side of L1, and the yellow trace, as soon as I hook it up to ground, which doesn't even matter really. day. Well, one of these days I'll get this to stay. Alligator clips with teeny tiny wires, not fun. There. Are you with me?
I am.
So yellow is the secondary side.
Yep.
So basically what I'm measuring right now the yellow trace is measuring the secondary back to ground,
Yep.
and the blue is measuring the other side of L1 through the capacitors and everything.
The other side of L1, meaning the side connected to the anode of the cap.
No, the free side that's free, not connected to anything.
Oh, right. Okay, got it. And then look at that. The final oscillations are out of phase with each other, but the T1 oscillations are in phase with each other.
Yep. We are playing with a lot of voltage right there.
Yeah, that's what those are 50-volt dividers, right?
100.
100-volt dividers. Okay.
Let me see if I can tune. Let's see, I'm at 16.2. Let me just see if I can.
The charger.
Hey, hold on a second. 1 second.
Okay. I think your back EMF is on the positive side.
All right, I'm back. One of my sons is not feeling well, so my wife has taken one of the boys to the stuff telling you that we were going to do before, and then I'm going to stay here.
Oh.
Ready?
It's kind of funny. One of mine is sick too. They're staying home. It's not funny, but
What's that?
both of my sons are sick.
Yeah.
They're not going anywhere either. So look, I flipped the leads on the secondary to hook them up to where they'd actually be hooked up properly, according to our schematic.
Say it once more.
I hooked up the secondary. I flipped.
Hold on a second. My wife needs me. I'm sorry. Right back.
Okay.
All right, I'm back. Okay, so yeah, my wife, who is a redhead, she like gets herself all flustered whenever she's got to go somewhere or whatever. Anyway.
I'm a redhead. So here you go. I flipped the wires on the secondary to be more hooked up the way our schematic should be accurately connected with the ground in the right place.
Mm-hmm.
And now they're inverted. They're the opposite.
Yep, they sure are. And for that matter, the oscillations in T3 are in phase now.
Right. Which is more accurate.
Yeah.
Now, if I remove the core or play with the core, check that out.
Yeah. That's
So
what
you
I
can
was.
get those in phase.
That's what I was talking about. Yeah.
So wait a minute.
That's why I think we can manipulate the core as part of trying to get this the negative side smaller.
Yeah, but you could also manipulate frequency.
Yeah, there's lots you can do with the core manipulation.
Well, look, they're both in phase. Step
Yep.
charging. Man, you know what I want to see? That peak, that blue peak right there is ridiculous. I want to see if I can connect a light bulb to the backside of this, like a neon, and get it to light, because it should right there.
But those are 100-volt dividers. Yeah, probably will.
Let's see here. I got our big fluorescent over here. Let me grab it. It's not that big, but bigger than what I was gonna get. That's some high voltage. That should light this thing.
Well, it's not 1,000 volts, but yeah, it should light it. It might. If it was 1,000 volts, it would light it without even touching it.
I'm not seeing anything.
I mean, it's only what, one, two, you got no more than 300 volts there, so it might not like that.
No, those are 100 volt. 1, 2, 3, 4, 5, 6. That's like 700 volts.
Oh, there's that many? Okay. Well, okay. I guess I was looking from 0 up, but you're talking from peak to peak, sure.
Yeah.
Hmm.
So I'm not seeing nothing like that. Now a neon would light at lower voltage, wouldn't it?
I don't know. If I think a fluorescent light would light before neon, but I might be wrong.
I don't know what I'm seeing there, but I don't know if I agree with it.
Agree with what?
Just the fact that it's, I don't know, not, because see, in theory, on the secondary side, which isn't even connected to anything,
Mm-hmm.
that's the yellow trace. I mean, I can get that amplitude pretty darn high.
Yeah, because it's all floating. There's no, well, the voltages are,
The neon is lighting.
yeah, I thought the neon would do at lower voltage.
I'm happy about that. I've never got a neon to glow on a circuit like this, I'm not gonna lie. Alright, let's turn the lights off. Now I can tune that in. Oh, I gotta hold the ground. I gotta be the ground.
Be the ground.
Let me actually hook it up to the ground potential over here so that I have some, not me as a reference. See if I can still make it work.
Yeah, with 700 volts going on in there, you don't want to be.
So look.
You don't want to be.
Okay, so see now I can't get those amplitudes anymore?
Yeah,
And that's
because you're not floating anymore.
Well, that's because the neon is grabbing all of my... You can't see that.
Oh, there's that. Yeah, I forgot about that.
Can you see? You can't see the neon from there.
I don't see it now.
Here, let me do this. Never fear. Portable logic camera is here. Let's get this guy over here. I don't have a long enough cord, but I'll stretch what I got. Can you see the neon? There you can see the neon.
No, I don't see him. That's okay.
Hold on, I just need to find out how to get 2 more inches of cord. Now you can see the neon. It's on my bench. See the neon?
Yeah, I see. I see.
Now when I move the core,
Yep, now I see it.
you get it to glow.
Very nice.
So that's good. That means that I am receiving and putting out high voltages, high enough to light that globe, which may only be less than 300 volts actually. Might even be like 150 volt.
Well, it's lighting it, not blowing it up. So
So what happens if I just, there you go, I can do the same thing with the other core. There you go, now I'm even getting more. There. The sucker's lit more than a single core.
Mm-hmm.
By adjusting these both.
Hey, are we still floating on both ends of the circuit, or did you close loop everything again?
No, it's floating.
And that blue and the yellow one is the secondary side.
Let me try something. Let me disconnect the globe. And see if I can use, there you go. Look at
Right.
that.
Nice.
So the blue, so that's why I can get maximum potential with both, which makes sense.
Yeah.
But there it is on the scope, so you can see it.
And that's your maximum.
That's like the maximum potential I'm ever going to get out of this thing. But that's through the water.
Yeah.
That's
Not only that,
that's
but-
fantastic through the water.
It is.
So I don't know what we need to do next, but there you go.
I was thinking about it. What we need to do next is
we need to route the energy coming from L2.
Don't forget, I don't have a diode in my circuit.
Yeah, I know. That's what I was just thinking about. We
I
need to
can
route
add
it.
it and see if we can see that same potential or half. We should, in theory, just see half of it.
Yeah, that's exactly what I'm thinking. We want to see the stuff going from the back of the backside of L2 through through the diode.
Oh, but don't forget, my secondary is not even connected at all.
Right.
Like, not even at all. So if I connect...
Let's hook the circuit back up, and let's see what we see.
You know
Hey,
what
while
I
you
want-
do that, I'll be right back. I'm going to check on my son who's sick.
Yeah, please do. Hey, you there?
I hear.
Look at this yellow trace.
Beautiful. That's what we want.
The yellow trace is on the secondary side of the diode.
Secondary side,
Of the diode.
the diode. Okay, so we're, on the anode of the diode.
Yeah, which is the line side, right?
No.
Well, let's see. Let me double check I've got this diode connected properly because I may have switched it, and that's okay. Let's see. Secondary side needs to be to that. So secondary side. So actually, I've got the diode backwards, but I'm achieving this amazing positive potential.
So that might mean let's keep it backwards.
Yeah, but the blue trace is across the positive side of the cell, so that's not good.
Okay.
But
Well,
let's
apply that know-how to the cell.
here. Let's flip it, just for fun, and see if we can get the same result.
That would be nice. I like how we deconstructed the circuit here by pulling it all apart.
Well, I mean,
It's great.
I'm at that point where I got to figure out exactly what piece is doing exactly what and why, because we're still not 100% certain on the bench of all these things.
No, exactly.
I'm at least seeing some fun stuff today. I feel at least better about seeing some fun stuff, because, man, sometimes I get done with the day and I'm like, what a waste.
Nah, it's all good.
So now I'm going to measure the secondary side.
Strong on the strong negative, huh? That's really interesting.
So now the diode's correct. So let's see if I can get the blue trace to be anywhere on the right side of the voltage potential. I feel like I'm in a science museum. Look at this fun wave go in different directions.
Yes.
Alright, so look at that. I can gain massive energy on one side, or I can gain massive energy on the other side. But I just cannot get that to do the right thing.
Go to a different frequency range. See if we can.
I was gonna do. That's what I was thinking. Right now I'm at 16.2. I actually want to go up first. I'm gonna set this exactly at 2300.
Yeah.
because that's the range at which everything seems to do fun stuff at last time I was playing with it.
Mm-hmm. I'm just thinking, yeah, you and I probably had the same thought of let's start resonating on the secondary side, which may be perhaps at a different frequency range.
So I can achieve.
Oh,
Look at that yellow trace. It's all
yeah,
negative.
that's nice. I mean, it's unipolar, anyways, just the wrong side.
Well, the yellow trace is the diode.
Oh, it's not on the secondary anymore. Okay. Which side of the diode?
It's on the secondary side.
Okay.
I'm not seeing anything fun right here. Let's try a lower. I can't get that. Look at that negative though. That's good.
That's what I'm saying. That's perfectly unipolar.
Yeah, it's pretty well. Let's try a lower. I don't know what that is. Let's try a lower. So I went from 16 to 23. Let's drop it down to like 9. I need to move this out of your way, I guess. Huh? Just turn it off.
Yeah, that's fine.
Oh, I'm printing something. Okay.
Yeah,
So-
I see it. Looks like there's a bunch of lights on in there that didn't used to have.
Yeah, see, that's part of my upgrade.
Is that just so you can look in and see what's going on better?
It's so the camera and I both can see what's going on better.
Nice.
I needed to make that one front. Going on there. Look at that.
Yeah, some good amplitudes on the
Serious amplitudes, actually. But
You're electrically connected, right?
yes, at thousands of volts. Well, not quite, but 700 something.
That's why I was thinking if it was not electrically connected, then it would be thousands of volts.
No, it's electrically connected. Okay.
That's how I measure it.
So that
That's
range,
how I get this. Go ahead.
that range sucks. I'm gonna do a different range.
Yeah,
I'm gonna go really low just for fun. Like 3.
3K.
Yeah.
That's my favorite range. I like it when things are down around 1, 2, 3K because that's when you get really nice fields.
Well, I never could get some real good potentials out of this circuit with that low of a frequency. Like, it just hasn't happened yet. I mean, I just can't get the amplitudes. I don't think I have a low enough inductance values, high enough inductance values, in my opinion.
Maybe.
Like the lowest I can get frequency-wise, you know, would be like right there in that range. Ooh, look at those positive peaks.
Yeah, those are good.
Ooh, right there.
That's what I'm talking about.
Let me zoom in. It looks like crap, but
Doesn't look that bad. It looks like low frequency. There's all that noise in between the pulses.
moving the secondary L1 side almost does nothing with the other core all the way in.
Okay.
But this one does a bunch.
Be the wiper blade.
So I don't know what this is telling me, but it doesn't look fun at all to me.
Kind of fun.
If I take these out, I'm gonna put this at about 18k, because I was liking that. Maybe I need to go up a little instead of a lot. Last time I went up a lot. Look at those.
Yeah, it's pushing it negative.
There it is, negative, almost the whole thing.
The whole thing. I wonder if we just flip that upside down.
Here, let me just flip the core over. Nope.
Yeah, flip the diode. Then the energy won't flow at all. What can we do though? What can we do to reverse the polarity on that? Well, that's above L1 anyways. We need it. What do we need it to do? We need it to. Oh. We need to put the capacitor between the blocking diode and the L1. Which doesn't make sense.
I know. We already tried that. So this now I'm like introducing like the cores are like, you know, on top of each other. Uh-oh. Broke a wire off. Where does that go? Oh, it goes to ground. Whoops. Hey, look. Okay. Yes, I really don't know what to do next on this particular path that I'm taking.
Well, let's see. Well, we want to get. Let's go back to the.
I like that 16-ish frequency, I think. Let's try a
What
little
I
bit
want
low.
to
It's
see.
like 1400. What?
I want to see when T-tube starts, a nice obvious pulse coming from L1 going to the anode. And we saw a little bit of that earlier, but it wasn't totally causally clear that it was like, no. So to do that, let's wire our circuit back up.
It's wired up.
Okay, I figured. And then,
Look at
oh,
that.
that's nice. I like how far below, but that's the diode above L1, right?
I disconnected the secondary on accident.
I like that. Look at that.
Look at that. It's like I can transfer the energy from one to the other.
Yeah.
It's like take the energy and that even looks kind of nice, but still not what I want. Let's put the yellow trace on the L1 side of the diode.
L1 side of the diode, okay.
Look at that. That's off the charts.
Yeah. It's off the hook, yo.
You know, I'm only at 6 volts.
6 volts input, that's pretty good.
Let's crank it up.
Mm-hmm.
Let's blow it up.
See what kind of gas we get.
We're at 12 volt. The negative side of this thing is disconnected, man.
Careful not to blow up your scope.
Yeah, I'm careful. Oh, I'm lighting the fluorescent tube.
Nice.
Barely, but it's there.
Getting some real voltages there.
Not really helpful, but I'm getting it. Alright, so this is the positive side of the cell, okay?
Okay.
If I can get this light bulb to stay there. Okay.
See slight bits of...
Hmm?
You seeing a slight bit of illumination? I can't see it in this.
Yeah, I'm seeing a slight bit of illumination.
Looks like it's about to fall.
It did. Hit me in the face, man. Okay. So now I'm going to put my tongue on it as the real test. There.
I don't want to
The old timers meter. Yeah, man. Let me check it. Oh, dude, it's totally like 480, dude. Yeah, that's a good one.
I don't even like doing that with 9-volt batteries.
On your tongue is weird.
I hate that.
So look, I have disconnected the negative. You know what? What would happen if I disconnect the negative from the earth? It won't have a place to go. That's probably a bad idea.
Sounds like a philosophical question.
I'm going to disconnect this from the earth. Let's see. I'm going to now attempt to get the negative side and the positive side connected to this thing. Golly, look at those things.
Crazy.
It's vibrating the other core. That's why it's jumping.
I can hear all the magnetoconstriction.
Wow, it's like sticking together almost. So what does this tell us now? More voltage? Oh, we're at 15 volts, 1 amp, 0.01 amp.
101 amp, okay. 15 volt, that's on the primary side, I assume.
See that, man?
Yeah.
It's AC though, I don't like it. Where's that little light? Ow, I think I just got shocked. Oh yeah, look at that, lighting that thing up.
Yeah, I can see it now. You got bubbles? You might.
See, I'm pumping water real slowly so I can see them, and I don't see any. Let's see what my meter shows me now that I got some really ridiculous stuff going on. It's dropping. That thing's almost down to nothing. One of two things is happening. One, that thing's hooked up backwards, and when I charged it earlier, it's discharging. Or two, the water is literally like neutralizing stuff.
Interesting.
So you know what I really want to do? I want to disconnect this scope so I don't blow it up. And I'll just... I don't even have the secondary side of the ground connected. See, that just kills it when I do that. What happens if I disconnect the ground from the other side? Okay, nothing. I can't hear it anymore. So let's try connecting the ground to this side. No. Try to connect the ground to this side. Yep. So if I earth L2, it seems to work really well. Ooh.
Probes aren't connected. You probably know that.
Yeah, I disconnected them. I'm just using this neon light as an indicator.
Yeah. Canary in your coal mine.
Because what I want to do is I want to crank the voltage up even more. Blow it up if I have to. I'm going to connect one side of this neon. Oh, I'm getting twitches in my skin.
Sounded like you got shocked from over here.
Did it?
I heard like a like a bug got zapped.
That might have just been my mic because it's wireless, but oh yeah, man, I can really make that neon glow. You see that thing glowing?
This is when you might want to take your probe off of your. Oh, you did that. Never mind. Yeah.
I'm gonna crank up the voltage even more.
But put the probe nearer though, so we at least can see, or change your scale.
It's pretty good actually.
Yeah, it'll read it perfectly. There's no diminution in the resolution. It's just not as much amplitude, which is good because it's protective.
So the probes in theory are back where they were. $20 volts. Oh my gosh. Oh my gosh, he's burning me. Hey, let me get this. Let me get this other camera, and so because the scope is basically useless. So let me turn. I don't need much of it. Let me turn this back on, and so you can see what I'm doing.
Okay.
So check it out. Check it out. So here's the neon. Wait a minute. Where are you at? There you go. There's the neon.
Yeah.
When I touch it,
Oh wow.
it's burning me.
I bet it is.
It's actually really starting to get to me. I'll crank it up. 23
But
volts.
yet you can't stop doing it.
Ow! Ooh! Oh, I caught the negative side with my hand.
Ouch.
I caught this right here. Let's check this out. What's going on?
Yeah,
Ow.
don't do that anymore.
Oh my gosh. I'm starting to feel some good tingly stuff going on. This is great.
Yeah, just be careful.
I should put my safety glasses on
It
at this
only
point.
takes a few milliamps to stop your art.
I'm gonna put my safety glasses on just for pure reference here.
And put your rubber sole shoes on too.
Yeah, I got actually. These are insulative shoes. That's from the positive side to the negative side. But you know what? I'm just not seeing any bubbles coming out of this thing.
Yeah.
Oh, my hair's starting to stand up. But, what happens if I connect this over here? But here's the thing. See, when I try to get any high voltage across the... Oh, I am getting some. Well, no, I'm not, I guess. There, I'm like shorting out the cell altogether, and I'm not really achieving anything. So, you know what I'm going to do for fun? I'm going to... Well, I can't do that because the cell is part of the circuit. Here, let's do this. I'm going to turn the power off. Okay. I'm going to remove the cell from the circuit, and I'm going to hook it up in another part of the circuit where I'm seeing high voltage. But actually, I'm seeing high voltage on the positive side of the circuit, so actually I shouldn't do that. Turn that on. I'm going to turn it all the way up. 30 volts. Ow! Oh yeah. It's definitely live, man. It's burning me. So here's the deal. Here's what else we can do. We can remove the pump. Pump is no longer connected. Okay, I'm going to hook this up in parallel. So now we can get past 30 volts DC. We can start working our way up to 60. Okay, so we're back at 30. Burning me quite nicely.
Yeah, careful.
Can you see that?
And I hear it when it burns you.
Hold on, let me put this down a little bit. We're grounding the LED out, or the neon. Oh yeah, throwing arcs. Look at look at that. Can you see that? Look.
I do.
It's,
Yeah.
no, that's moving.
If nothing else, these some nice coils.
They haven't shorted out yet, huh? Wow. I'm not even like tuned into a frequency, right? I'm just plugged in a random frequency.
Random. I mean, we dialed it in.
Not really. Oh yeah, dude, it's like biting me. Ow! Feel it in my cavities. Yes.
And you keep going back for more.
Where are we at? In theory, that's about as maximum as I want to go. We're only pulling 0.7 on each supply. So at 0.8, we're pulling 1.4, 16, 1.6. So there we are at 200 milliamps. That's actually 160 milliamps. And I just am not seeing any bubbles. Golly, that's loud. So let's hook the grounds back up. See, that like kills my neon. Well, kind of. I'm smelling stuff. Or if that's my...
What do
The
you smell?
primary's
Like,
still cool.
like ozone smell or burning electronic smell?
Where can you see this at? I'm touching the neon down here. It's lighting up pretty good. Let me try the fluorescent tube now that I got it this high. Not much out of that. There we go. You see it lighting up?
Yeah.
I can touch it just about anywhere and it lights up. Lights up real well right there. So, high voltage, yes. What else though? Now where do we sit? I'm playing with high voltage, that's kind of scary. You see that?
Yeah, I do. High voltage is good, but it's
It's not helpful at this moment.
not helpful at this moment. Yeah, what we need is to master this continuous conduction mode thing.
Alright.
And I have a feeling when we do, all the energy that's on the negative side of the oscillation will be repurposed for the continuous conduction mode operation.
Yeah, can you see that neon?
I see it,
Yeah,
yep.
see it. So let me connect this back up on a single supply. So there, I can get the neon to light between the positive and the ground. So basically just through the water bath back to ground to complete that circuit, I can create very nice high voltage at 7.5 volts in, and I'm reading practically nothing on the input. I mean, I can't read it on that meter, and this meter doesn't seem like it's reading things in the right manner because of how we got it connected, but it's minuscule.
Yep.
So, we'll leave it at that and plug in my scope. And there's what it looks like.
Yep.
That's huge amplitude. That's not 1,000 volts though. We can
Right.
dial it into right at about 1,000. There's about 1,000. 8.4 volts down. 7 volts. There's the yellow trace.
That looks good.
Yellow trace is on the... You know what I'm going to do? I'm going to hook this trace up to the other side of the neon. There you go. There's the other side of the neon. So from high voltage, so from the positive probe through the neon, that's the yellow trace.
Okay.
It's a lower amplitude, obviously. So then how do I get... Whoa, look at that. Off that gate time, we keep talking about the gate time having them funny looking pulses and stuff. All right, so that was fun. I like the feeling of my teeth shaking. The cavities are, you know, useful for certain things like detecting high voltage.
Yes.
So now what?
Now it's really about, we got to get this continuous conduction mode dialed in. I think it's going to solve a lot of our problems. So that's the thing I've been working on over here. I didn't actually stop working on it since we've been looking at since I've been looking at your scope because it's been fun. But I guess as I resume this evening, I'm going to continue on that, getting this thing balanced, getting calculations that make me think it'll work, and then spending all the energy to hand wind in my coils. And then doing some testing. And I'll share the specs with you as soon as I have them ready.
So exactly what should I try to achieve now? And I don't know the answer to that question.
Yeah, continuous conduction mode with what you have should be possible to some extent. I think we saw it to some extent today. But what I really would like to see is a clear T1 off, and then see a response from the coil instead, you know, of, and maybe that's just a difference between digital and analog scopes or something.
Well, I think there's some problematic stuff going on there. More chicken. You haven't eaten like all day, have you?
I didn't. Yeah, I gotta eat something soon.
Well, go eat something. I'm gonna eat some chicken. I'm trying to figure out.
It's 6 here. I've got to like start gearing up for kids coming over and stuff. I'll probably. I mean, I could be a what do you call it? Like a Grinch type, but for Halloween, and just turn all my lights off. I don't want to do that.
Or put the candy outside.
Yeah.
No.
And Griffin's sick anyway. He probably doesn't care what happens. He's not. So I don't know. He's just like laying in bed feeling terrible. Poor kid.
So I'm just trying to figure out exactly. I mean, I was pretty much in resonance actually right there at that frequency. I just must have dialed it in.
Yeah, that's what I'm saying. There's no way it was just accidental. I mean, maybe it was accidental, but what I mean is there's no way it wasn't resonance.
Yeah, because I've been moving these cores around, but it just happens to be that if you just sit them in there, this is a pretty good frequency. But look at that, like, I can completely kill. Does that change this? Let's see. So, the neon's telling me that the signal on the scope is very accurate. when I adjust it. I just don't know, man. Look at that. Yellow traces went off the charts.
That's by adjusting the core, right?
Yeah, I gotta adjust both of them to get it there. Which is totally fine. And, oh yeah, so I can move it?
Yeah, totally.
But
you can even move it to the extent that you can move just the negative side. That's what I've been able to do, and that's what I was hoping we could do in yours to some extent.
Yeah, but were you not? But how are your coils connected? Because right now, you know, I just wonder if I should try, for total fun, putting the inductors on the same core.
Yeah.
And the primary secondary on the other core, and just see what happens.
Yeah, why not?
I don't recall actually flipping everything around just for fun. But because that's not the way.
Well, I mean, it doesn't hurt to be, you know, just explore. So yeah, do it. Look at those swings I had T3 on the yellow side. Those huge swings on T3 from the yellow side.
I know. You know, and I can get. Look at that one. I mean.
I know, that's crazy. It's like free to just. It's just free to go nuts, and it does when you have it that way.
All right, so let's move L1 and the secondary. Now, the thing is these two, let's see. They're wrapped in the same direction, they're on the same core, the same direction, but they're connected backwards. So, okay, so that makes sense. So I'm going to pull out. That's the wrong one. But see, the thing is even on the VIC with all of them on the same core, which I tried to play with, I still couldn't get anything out of it.
Oh right.
You know, that whole time though I was playing with this, I had that secondary side of this disconnected.
Yeah.
The secondary ground was totally disconnected.
Yeah. I've definitely played with that before. When they're floating like that is when you get the craziest voltages, no doubt about it.
Okay. So these are still accurate. Because this will allow these chokes to really do their job, and the secondary side of this circuit do its job as a step-up transformer and then an oscillator. So we'll see what happens here.
Mm-hmm.
Alright, got those switched. I love that high voltage. That was fun.
No, it was.
I haven't got like that high amplitudes out of this thing yet.
Oh, cool. Good.
Not like that, because you know you're talking about like 40,000 volts, and I've not yet ever seen anything over 2,000.
No, I'm telling you, you can, especially when you start. We were just looking at forward EMF there. Well, actually, that was back EMF too.
all those oscillations. Yeah, and that's when the voltage gets nuts.
Chicken. Okay. Diode needs to go to the F of the S. F of the S. And then I kind of have to connect that. I can't let the secondary side of this thing float now. I guess I could.
But it, the thing is when you connect the back end to L2 to the positive side of L1 to the positive side of the secondary, it is still floating, and that's why the voltages can still get crazy.
Okay. Okay. Turn it back on, see what happens. Nothing. Okay. Where should I hook my probes?
Let me see.
We'll put one back on L1. We'll put another
On the gate.
Oh man, okay.
Gate's very orienting.
Wow. Let me double check my connectivity here. Positive at L1 is S, the way I'm doing it. L1, S, yep, that's the way I got it. Negative is F, which is correct. Secondary goes that way. So secondary. Okay, it's all right. I didn't put the other half's cores in either. All right. There it is.
What we got there? Same frequency?
Yeah. It's not drawing.
There.
It's not drawing.
Dialing in a little now.
I'm just turning up the voltage.
Okay. Well, let's go ahead and zoom in a little and see what's what.
Let me bring this down to like 5-volt level. Turn this water down a little. It's so loud.
Yuck.
I need to connect my ground on my circuit though still.
Okay.
That's why it's floating like that. There we go.
Much better.
I'm putting 5 volts in. Let's go back down. Start
Yeah.
back at 1 volt and play with it since we saw what we saw earlier. Let's see what we see now.
Yeah.
And actually, I'm still... You and your gate, which is fine with me, but makes me laugh. Okay.
I'm glad it's found you, and I'm glad it amuses you.
Alright. Let's just go for a big frequency sweep here.
Gate's nice because it tells you exactly what's happening at your MOSFET.
I know, it's a good thing. It's just... I'm visualizing what's happening because I'm looking past it. I can kind of see what I'm seeing. Alright, we're going to sweep pretty fast. Depending on how fast my computer will think with all this other stuff happening, but...
You think you're seeing what you're seeing, but you're not actually sure.
Well, yes and no. I've been playing with this for so many weeks now that I have a pretty good feling of exactly what I'm looking at.
Yeah.
Then again, it's not what I want, so it's okay though.
Right. I've been playing with it for years, and I know that it's really good to keep an eye on your gate.
Yeah, you're right. I'm not arguing the point. Getting there. It looks to be about right in here. Yep, it's going back down now.
Yeah, so that's good. Just zoom in there. Let's see what we got. I mean, we know what we got, but let's just look at it real quick.
I'm going to put a couple more pulses on there. It looks like it's trying to grow. There's 25 pulses. Let's do a big 50 and see what happens. See where it peaks out. I'll leave it there. So, oh no, don't be screwing up on me.
Well, if you got to make it less pulses, that's all right.
No. I better knock the wire off. Hold on. There we go. So, what do you want to look at? Look at that weird big oscillation.
Yeah, I see it in T3.
What's up with that?
It's interesting. Yeah, that's good. Okay, so pulse on. Pulls in, pulls it back down. Pulls it all the way down, though. Like, it's weird how it's swinging as an independent variable. It's got to be it's got to be just the way that the digital scope works or something. I don't know. It's just strange to me.
I'm at 1 volt. Let's go up a little. Hmm. 2.3 volts. There's 5, 6, 7, 8, 9.
That's 1,000 right there?
10. Yep. 11. There's 12 volts.
12 volts puts you at like 1,200?
Wonder if I could even go more. No, it's about peaked out. I'm actually going to take some of these off. I'm going to bring this back down to about 35 pulses. And I'll bring it up a little bit. Let's do 40. I'll keep it there. So yes, I'm over 1,000 volts. See if let's see, just for fun, let's see if my neon's going to light up. It's a swing though. It's not what I'm looking for.
Exactly.
Well, let's just see.
Took some voltage down when you put it on.
I think it's because of the capacitance. Oh yeah. I'm lighting the neon really well. But, of course, I'm not lighting the neon across the cell. See, look, when I short the cell out, amplitudes get higher.
Mm-hmm.
I'll bring the voltage down a little bit so you can see the whole thing. Times 8 volt. 8 volt is still giving me to ground, which is why it's shorting out a good light on the neon. So we definitely got good voltages there.
No doubt.
Now what should I do?
All right, so continuous conduction.
Playing with the cores here.
Zoom in for me.
Yeah.
Okay. What'd you just do there that changed the amplitude so drastically? Just moving the cores?
Yeah. I mean, I tuned
It's
it in.
like it's biggest, yeah, it's biggest when you have it such that.
I tuned it in that way though with the frequency. Like I could adjust with these and then adjust frequency and tune it back.
Mm-hmm.
Actually, I'm gonna try that. I'm gonna take the core completely out of the primary, secondary side.
Right.
And see if I can get anything out of it. Because I'm curious. I'm actually going to go up in frequency. It's probably the way it's going to like me.
Towards the question of conduction, continuous conduction mode, I guess we'll see. We should see much smaller.
There, look. Look.
Yeah. Uh-huh.
That's all positive potential.
It's more unipolar. Zoom in on that.
Yeah, well. There's that double pulse.
Yeah.
See, that double pulse is important.
And there's no core though, huh?
Not in that side of the circuit. See, look right there. So that's what I wanted to do. I just wanted to see if I could. I took them out of both right there.
Put it back in one side again for me. What side is that?
That's the inductor side.
Inductor side. Which inductor?
Both of them. Same core.
No, I know, but I guess I'm talking about L1, L2.
Both. They're in the same core.
Oh, you rearranged the circuit. Okay.
Now, if I take that out and just put it in the other ones. I would like to,
That's nice right there.
let me see if I can tune that a little more fine with.
I like that.
I know I don't think it's like really in resonance, but it's more of an accurate. And actually, you know what we could do? You know what I need to do? Let me do this. Watch this.
Frequency dial.
Let me dial this in a different way. Okay, I'm gonna say that's about right. So let's put about 10 pulses and then take away some of this timing. Let's go with 800.
Is this the P-Gen tool that you're energizing with?
That's correct. Okay, let me put this on 1 and add a few more pulses. Only a couple. Let's zoom in.
All right, here we go.
See, those first couple of pulses are almost like.
Continuous conduction with no core, huh?
Yeah, on that one side.
It's weird.
But now the real trick, let's turn up the voltage. I'm at 8 volt right now. Look at that little ripple in the front when I go up, down. You see that?
I do.
It's weird. that's like 18 volts.
Can you zoom in a little for me? Okay, that's nice. That's really nice. Off, swings crazy up. Comes on, pulls it back down. But then that second ripple doesn't make a lot of sense there.
I'm going to adjust it some more. Now that I changed the voltage. See, like when I'm adjusting this, which way do you think is better? See, I don't like being so close, because I can't see the whole wave.
I know.
You know, that's a funny looking waveform right there, but that's actually a very good looking waveform.
It is.
Like, it doesn't look like a resonance, but
It's not pretty, but
it looks
it's
like
got a lot-
something I would
It makes
want.
a lot of sense, yeah.
Yeah. It looks like something I want to see. But, see, I'm removing, well, once it starts thinking. Hold on. There we go. This computer's so slow with this stuff ready. Okay. Big frequency sweep. Here we go. I'd like to see all those. It's out of resonance, which is why you're seeing that double peak, but I'd love to see that double peak on every pulse.
Exactly.
Kind of like that.
Yeah, but and then higher.
But yeah, but bigger.
Put the core in. Might make it bigger.
I made it bigger.
Makes it-
I just
Makes it bigger, all right. But it cleans up that impulse completely.
That's just not. That's 100-volt peaks too. 100. That's over 1,000 volts.
Coil loves that core.
Well, to have a nice resonance, but I don't like it. I just don't know. I mean, it just brings it into resonance, which is great, except
Well, no, it doesn't. It doesn't bring it into resonance because it's a part. Resonance doesn't have anything to do with the core material, but it does at the resonant frequency create a lot more potential for induction because of the. Go ahead.
I mean, I'm adjusting into the resonant frequency via inductance. That's what I'm saying.
Oh yeah.
That's what I mean by what I said, I guess.
Yeah.
And when that core bounces around like that, that's some fun stuff. Look at those peaks. I can't even see.
I know.
Look at that.
It's huge.
That's over 2,000 volts right there.
And that's directly electrically connected.
Yeah.
You might want to not do that. 2,000 volts is probably the limit of your scope.
Yeah, you know. It's just for a short time.
Yeah.
I'm telling you, I've tested this scope through a lot of stuff, and it is happily taking what I've thrown at it. Alright.
You just don't want to lose your scope.
No, that'd be bad. And then again, in the name of science, sometimes you just gotta make it work.
Got to sacrifice your scope every now and then.
Alright, so continuous conduction mode. Ooh, that's pretty.
That's ground.
Okay. Threw my ground off.
Continuous conduction modes is all about a balance of the core. It's all about a balance of the field that's produced when the thing is energized, and a balance of the pressures behind it when it, minimum of pressures behind it when it collapses. That's the whole trick. So we are, I mean, I really feel like just based on what we have right now, we should be seeing some of it, and maybe we are, but it's just not. It's not like totally compelling because it's so small, and also the way the energy swings in your scope is different from the way that it swings in mine, which I can't understand how that could possibly be, but it seems to be the case. In mine, there's a definite relationship between the cause and the effect. In yours, it's like the swinging average, which is cool. I like that actually, but it's just different, and that's what I'm struggling with, trying to understand why that is. Is it because it's doing math? It's not really representing the electrons, but it's doing math on it and then representing something, mathematically in graphic form. That's what I feel like must be going on.
There, that's 1,000 volts, okay? I'm not connected anymore. Man, that core on that primary, secondary side really starts vibrating. Just goes crazy. Throws the current way high. Just weird stuff when that happens. Maybe it's because it's throwing out a magnetic field that's interfering with stuff.
Maybe it does. I mean, this thing puts out a pretty good field. These cores do. But I've been measuring. That's one of the parameters I've been measuring on the Gauss meter, and it's pretty awesome. Pretty awesome core.
Oh man, this is not gonna be a good idea. Yeah, so I can achieve. Yeah, so according to the scope, that is 1,000 volts. So that's over 2,000. Man, that one vibrating is crazy. I smell something.
What are you smelling?
I swear I smell ozone.
You might because of all the high voltage.
That's not the first time. Man, it's strong. Like right there. It's sucking that core in together. It likes to be together. Let me put in a core that has a gap, because actually that's what I want, is that little bit of a gap. There we go. I actually want to see that.
What I do is I just kind of like don't touch them all the way together. You leave a little bit of space between them.
Yeah. That's what I got right now. I got tape. I don't know, man. I'm just pissing in the wind at this exact moment in time, but
it's all right. I mean, yeah, because I haven't yet figured out how to get engineered continuous conduction mode on my side either. So until I have, I'm all I can do is look at this with you and try to understand what's happening. But that's what I've been spending to the extent to which I've been able to spend time on it this week, which wasn't that much, but I do plan to spend a lot on it this weekend. That's it. We got to master this piece. I feel like it's important.
So I'm at 30 volts, and this coil is ice cold. This primary coil.
Yeah, I'm not surprised by that. You're not running any power through it.
I mean, but even at 30 volts, it's pretty good because usually it. Let's
Volts are cold. It's current that starts producing heat.
No, I know. I mean, I'm just saying for. Yeah.
Yeah.
Let's go with more voltage again. See what we get out of this sucker.
Okay.
Remember, the scope is not connected. See, it gets to a point where it just freaks out.
Yeah.
Oh, jeez. Scared. Golly, that thing is sucking itself in hard. Got some serious stuff going on there.
It's sucking it in?
Yeah, like I can't even pull it out. I can lift up the whole thing.
Wow. Like, so it's like magnetically attracting itself.
Yeah.
Yeah, that makes sense.
Watch. This, I mean,
It is a magnet after all.
Yeah, but it's like super
Strong.
ridiculously, strong.
Yeah, it's probably a couple of hundred of Gauss. That's what I've been finding. And yours are way stronger than mine. I mean, a couple of hundred Gauss is, up there with permanent lower strength permanent magnets.
See, it gets to a point where my power supply actually freaks out.
Oh.
My power supply jumps around and throws out a bunch of current somehow. Like, it's still cold. Just keep going. I don't want to melt my core again. I melted in one of my cores one day. That was kind of interesting.
You melted it?
I melted the core because I got too hot. It's pumping a lot of current through it.
Oh, okay. I actually love working with these coils without current because it's like very safe and it's like all these cool weird effects.
Yeah, exactly. So, what I'm finding out right now is no matter how the coils are arranged, as long as the circuit's connected correctly, I can still achieve the same potentials.
Mm-hmm.
Golly, I can smell the ozone. Let's see if my neon lights up.
Love the smell of ozone in the morning.
Oh yeah, I got lots of that. The LED's lighting, or that neon's lighting nicely. I can feel it, like heat, burning my finger.
Really?
Yeah, it's not a normal shock. It's actually burning. Ow, that is crazy. Ow. It's not the same type of high voltage shock that I'm used to. I've shocked myself plenty of times.
Be careful. Good thing there's low current.
I can actually see the arcs jumping into my finger.
Ouch.
Ow, burn me. So even though the scope is kind of lying to me in a way, the neon bulb is not. The neon bulb is like telling me I have more and more high voltage, even though the scope doesn't show that beautiful, nice wave.
Mm-hmm.
Oh my gosh. Yeah, the neon is telling me the otherwise. Oh. Yep, killed something. Ooh. Oh. Hot. Oh, dang it. Melted my scope. So much for connected to the gate.
Oh, really? You hurt your scope?
The MOSFET. It finally fried.
Oh, okay.
And my scope was connected to it, so it got a little melty. That's okay. This might be the same.
You and I always do is take a breadboard cable and just connect the probe to that.
Yeah. That's okay. This is the same probe that went up in fire that day, so it's all right.
Okay.
So I burned my MOSFET up. Let's see if the core. I want to see if this is hot at all. The coil got a little worn, but not enough to deform the form. So that must have just been back EMF into that thing that got it hot. I don't think it was the current, because that coil would have popped.
Yeah, it was definitely the backing up.
But what about my I have two tiny diodes, resistors on here that I'm using for impedance matching. They're ice cold. They're only a 1/8 watt. Okay, well.
Yeah, man. Good enough for today.
I'm turning that off. What time is it? It's 3:30 anyway. You probably need to go. I need to get my stuff cleaned up.
This was a good day.
What did we learn today?
Well, for one thing, we learned like weird stuff about the capacitive discharge during that period of time when the plates are still high voltage enough, but when they still have enough of a voltage to kind of interact with the water, that there's that effect, that really cool effect that we observed today. And
that's pretty interesting.
That might teach us something about the interaction of the plates with the molecule itself. That could be really important. So anyway, that's a really cool thing. The next thing we learned today is that, well, we didn't learn it so much as we kind of just explored some of these ideas around continuous conduction mode and around, looking at the frequency during T2 and T1 through your setup there. Also, kind of confirmation of these coils we're building with these new winders that we have on our benches. I don't know. There's a lot of good stuff just in terms of that. So I think it was a good day.
I agree. I like being shocked.
But yeah, we learned that you like being shocked.
You know about the story with now I forgot her name. Somewhere. What was her name? She could pick up the radio stations with her teeth.
Oh, Lucille Ball?
Is that who it was?
She was able to pick them up with her teeth, and she went to the dentist or something, and she thought she was crazy for a while.
Yeah. It was just like the 10,000 watt station that was like right next to her place or whatever.
Yeah. That's horrible.
Interesting. Oh, that's free music, without tuning in. I think it's all right.
Exactly. Walk around, just enjoy the music. That would be annoying, though.
Okay,
Especially,
well. Yeah, well, yeah.
I was just commenting, especially if you didn't really know where it's coming from. It would just, kind of freak you out.
Yeah, it really would.
All right, man. So I'm gonna keep on with this, with my attempting to master the concepts of continuous conduction as it relates to Vic, and eventually I'll be in a place where I'll say, okay, here's what I think, and here's what I'm gonna wind as the results, and that's what I'm gonna really try to drive towards. I'm also gonna try to pick back up the streaming thread this week, and so that we can make some actual progress on moving towards that by next Friday.
Okay. Sounds like a plan. I'm gonna clean up all my crap. Finish half the videos I started. I think that's where I'm gonna focus on for the few.
Cool. All right.
Yeah.
Well, I'll catch up with you soon then. We'll talk soon.
Okay. All right, Alex. Have a good day.
You too, man. Bye.
All right, bye. Thanks, Jim. My computer is so slow with that Skype. I'm capturing all my screen. Oh man, that thing was eating me up. Some good high voltage going on there. See how my 3D printer looks. Oh, the part done. See how this one turned out. That one looks pretty good. Alrighty. Turn that off. Turn that off. Clean that stuff up. out the door. Guess that's it. Been fun.